Hello. Good morning, everyone, or good afternoon, or good night, regardless where you are. Welcome. And welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support, without which the summer school wouldn't happen. And I'm extremely happy to see you all here today, both on Zoom and on the parallel session on YouTube. And I would like to note a couple technical and organizational details. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself and do not turn your cameras on unless you have a question. We really ask you to put questions in the chat. That way it's going to be easier to handle the questions both for the instructor and for the TAs. But if you really want to speak up, you can raise your hand and then we will let you ask your question live whenever there's going to be a good time. And in that way, you will be able to unmute yourself and turn your camera on if you want so. If you're in the YouTube session, you can leave your comments and questions in the live chat, and we will try to handle them as fast as we can, either by answering the questions ourselves or directing the question to the TA and to the instructor. And I should remind all of you that today's session, a Zoom session, is being recorded. And I'm thanking you all in advance for following these instructions and the rules. And we shall move on to our 9th workshop in this summer school series. And today we're moving to the series of sessions in the natural language processing. And today it's going to be natural language processing text classification, excuse me. And let me introduce you Professor Dirk Hovy. He is an associate professor of computer science in the Department of Marketing at Bocconi University and the director of the Data and Marketing Insight Research Unit at the Bocconi Center of Data Science and Analytics. He works in NLP, natural language processing subfield, and also the subfield of artificial intelligence. His research focuses on computational social science, and he's interested in what language can tell us about society and what computers can tell us about language. And without further ado, Dirk, the floor is yours. You can share your screen now, and thanks everyone.
Thank you, everybody. Thanks for the lovely introduction. Very happy to be here. Good to see so many of you. I hope this is going to be useful and interesting to everybody. As an administrative note or organizational note, whenever you have questions, please ask the questions right away in the chat. They'll then be relayed to me and I'll answer them right away. So if anything is unclear, ask away. This does not presume that you have any prior knowledge of NLP. But, you know, we're a very homogeneous crowd, so a heterogeneous crowd. So, you know, like people have different backgrounds. Some things might be super clear to you, but they're not clear to somebody else and vice versa. So whenever there's a question, just, you know, ask away. Happy to answer questions at any point. Okay, let me share my screen. So here we go. All right. So let me start to frame this a little bit. I mean, I assume you're here because you're interested in natural language processing, but just to tell you a little bit about, you know, the scope of what is going on. Since you woke up, you've started reading things in one way, shape, or form or another. That includes your morning newspaper, be that digital or analog. That involves emails, that involves blog posts, but that involves also things like advertisements on the side of the road, the names of streets, little tidbits here and there, stickers on lampposts, whatever. So you get to around 9,000, maybe 10,000 words a day. Over the course of an average lifetime, excluding the first few years where you can't read, that gets to around 200 million words in an average life. Maybe if you're a professor of comparative literature, that, you know, gets a little bit more, but even 200 million is pretty impressive. However, if you actually look at what that means in terms of data, you could store all of that on a regular, you know, memory stick, less than half a gigabyte of data. That's, you know, essentially nothing today. So all your life's worth of reading, less than half a gigabyte. So Compare that with the amount of data that's generated each day, which is 44 billion gigabytes. So, like several orders of magnitudes more than what we can read in a lifetime. Obviously, impossible to process that manually by, a single human being, even, like everybody together. So we need help with that. Also bear in mind that, this grows exponentially. The part that is growing most is unstructured data, which are things like text, things that don't come neatly organized in columns and rows and whatnot. So NLP can help us make sense of that. And I'm going to talk about today about some of the things we can do. Tomorrow, I'm going to talk about topic models and a little bit about the background and how we get there and the things we need to do and to know, but also some of the caveats. So part of this whole affair is that, big companies have taken note. Probably since you've gotten up, you have used one or more of these things that actively make use of NLP technology under the hood. So, you're contributing to this field being the huge industrial success that it currently is. That wasn't always the case. When I started doing NLP, there was no sense that this would be, really industrially viable within a reasonable amount of time, and then suddenly it exploded. Now, one of the parts that's actually most successful is classification, and that's what we're going to talk about today. Some of that is, for example, the most well-known probably sentiment analysis, where we use something like reviews or other textual input, and then we want to classify those as positive, negative, or neutral. These are used widely in business intelligence, market analysis, opinion mining. You want to find out what people think about your company or about other companies or about a sector. So this is really, really useful. There's also hate speech classification. This has become, unfortunately, a pretty huge sector where we basically want to monitor social media and flag things that could potentially be hate speech. Obviously, all of these things, hate speech is a complex phenomenon. It's not a simple yes or no, but it can be, helpful to flag something and have it then analyzed by a human analyst, by a human moderator, to see whether something violates policy of a platform or whether it's actually harmful. There are also uses for mental health. So people are trying to develop systems that can assist psychologists in, assessing the mental health, for example, suicidal ideation, depression, PTSD, of at-risk patients by, for example, monitoring their social media output or other written communication. So there's a wide range of possible applications of these classification tools. They can also be used to tell you more about individual users. There's a sort of frequently used task called geolocation. If we want to know where a message was sent from, roughly, it could be just the country, could be, more detailed down to the city level. You can do something called geolocation, where given a tweet history of a user, you want to, roughly pinpoint where they're located. This can help in social media analysis, but also in things like disaster relief, has been proposed for things like droughts, earthquakes, hunger situations. So as a little explanation why this is useful, I've said how many tweets there are, but if somebody wants to actually find out, they could go and read about who they are, but soon, if they're a reasonably popular company, that would be too much. So the idea here is that we can automate these things. We can just run everything through a computer who does not care how much data we give it, is much faster than a human in processing large amounts of data and doesn't get bored with it. Then we can get like an aggregate answer. So this hopefully can make our lives easier. Now, in everything we're going to talk about today, and in the first half of the session today, I'm going to talk about the background and the theory behind it. in very broad terms. And then in the second part, we're going to actually implement it. We're going to go through a Colab notebook together where I show you in Python how to do text classification from scratch. But whatever we want to do, there are these 4 steps that we need to bear in mind. First, we need to take the data and we need to pre-process. We need to make sure that it is in a shape that we can use. We need to remove any noise, any unwanted information, and we need to sort of like focus on the things we actually can use, the parts in the text that we're interested in. We're going to talk about that in a bit. Then we got to choose a text representation. So obviously, we as humans are capable of reading text in a variety of languages and script systems. But to a computer, all of this means nothing. Underneath the hood, computers, still work in binary, so on or off. It's just a long series of circuits that are flipped on or off, represented as 1, 0. And we need somehow to translate the text that is in English, German, Chinese, Italian, whatever, into a format, into a representation that the computer can read and that we can actually use to run a classification model on. So this is the question of representation. Then once we have it in that format, we need to select a classification model. We need to use some sort of classifier. In most of what we're going to talk about today, I will use logistic regression as an example for 2 reasons. One, logistic regression is pretty widely known. It's widely used also in social sciences. So this is not, some arcane algorithm that nobody has heard about. The other reason is, though, that it's still extremely powerful. So we will see that like a very simple logistic regression model actually gives pretty good performance. Now, in selecting a model, there are a couple of parameters and a couple of procedures that we want to use. One of the important ones is cross-validation, because we're interested in predictive power. We're using logistic regression in a slightly different way from how it's used in social sciences, where we're more interested in explanatory and causal models, whereas here we're trying to maximize the performance on a held-out data set on unseen data. To measure that, we're going to use a bunch of different metrics. And then we're going to talk a little bit about regularization, reducing the risk of overfitting or, sort of like latching onto faulty explanations. Was there a question in the chat? I think I saw something flare up on the screen.
Yes, so there's questions on one of the things you mentioned, which is geolocations. How would it work? Would it work via named entity recognition, or how exactly would that work?
Good question. So named entities do play a role. Named entities, for those who are unfamiliar with it, are proper nouns like, Dirk, London, Milan, Mona Lisa, dollar, that refer to entities in the real world that are classified in a taxonomy into things like person, location, organization, work of art, other things like that. It turns out that one of the most indicative things for where you are things like the names of landmarks, parks, or other things. The names of sports teams. You tend to talk about the sport team of your local area more than about other sports teams, but also names of local politicians, local celebrities, and other things like that. So named entities do play a big role ultimately for the precision of this geolocation. But there are other things, for example, if you're using, localized slang or dialect versions of words or other aspects. So there's a lot that goes into it, but named entities, we've done a study on that, actually do play a huge role and have a huge importance. You tend to not talk about, let's say, Milan as much if you're not in Milan. When you're in Milan, there's a much higher probability that you talk about it. Mm-hmm. Anything else?
That's it so far. Thank you.
Okay. So here, so there's, plenty of extensions to everything I'm going to say. I really want to go through like the minimal viable approach. There are, you can always get smarter, cleverer, better, more targeted with what you want to do. And to some extent, you have to do that, right? So domain knowledge, expertise in the thing you are studying is still very important, even with more and more powerful models, even with neural networks now that have, fantastic capabilities of like generating real looking text, translating text to speech and vice versa, translating from one language into another. You still need knowledge of what you're doing. And, for many of you as working social scientists that want to use classification as a tool, it is even more important to be aware of the quirks, the idiosyncrasies of the particular topic that you're dealing with, because that might make it necessary to include some things but not others, or just completely ignore certain words because they're sort of too ubiquitous in what you're looking at. So we're going to work through all of these different steps, and I'm going to give a few pointers and backgrounds. There's a wealth of literature in on classification, on NLP. I have sent out a couple of links. I've also just published the first part of 2 books on NLP, textbooks that came out in Cambridge University Press. First one is more on analysis and exploration of text. The second one that hopefully comes out later this year is going to be on classification in various different ways. One thing I'm not going to talk about today is neural networks, which have become super popular, but they actually, require a much longer ramp-up time and a lot more background. We're going to dip a little bit into it, but actually, logistic regression is sort of like a very simple version of a neural network. So you could even say that we're going to talk about neural networks today. There was another question?
Nope.
Okay. Okay, then let's get started. So I want to talk a little bit about the background, how we got here. Then I want to dive right into pre-processing, what it is, why we do it, learn about bag of words representations and continuous representations, and a weighting scheme, TF-IDF, that sort of helps us to emphasize important words more and de-emphasize less important words. So we're not going to weigh each word the same, but we're going to, make differences. Some words are more interesting than others. And I'm going to introduce 2 methods that are sort of based on neural networks, on representational learning, that are often used today to represent text as input. Okay, so let's start with pre-processing. Basically, what we want to do in pre-processing is we want to take the text that we get from whatever source we have, from the web, from Twitter, from, like a party manifesto, and we need to strip away some of the indentations, some of the markup, some of the, things that basically just make it visually more appealing, but that actually do not contribute to what we want, right? Or what we want to work with. So as an example here, for example, we have text that we've scraped from the web, right? And it's between div tags, which, help something with the formatting, but we're actually less interested in that. What we want to do with pre-processing is kind of strip away some of the noise and get it into a format that we can use that sort of leaves us with just the juicy bits, just the information bits that we want in the text. So we want to minimize variation. So we want to reduce the vocabulary size, the different words that are in there, while still maintaining all the information that we need for our task. Now, I should say right from the start, this process requires some knowledge about what you're interested in. So if you're doing sentiment analysis, maybe you're not interested in numbers. You can just ignore all the numbers. Obviously, if you want to do an analysis of the financial transactions of a company, numbers will be very important. So in that case, you don't want to throw out numbers, right? If you're interested in geolocation, as I said, names are super important, so you want to keep them in. However, things like prepositions, articles, pronouns are probably not going to be helpful, so you can throw those out. You can also ignore uppercase, lowercase. If you're interested in determining whether a text was written by person A or person B, which is something that's done in forensic linguistics. For example, if you have people who are sending out bomb threats or kidnapping notes, ransom notes, then you want to say has this text been written by one of the suspects? But it can also help identifying historical authors, for example, to determine, is this actually written by Shakespeare and we have discovered a new masterpiece, or is this forgery? In that case, you might actually want to use prepositions, pronouns, determiners, because they're a little bit like a fingerprint. Everybody uses them in their own idiosyncratic way without being aware of it, which is the good thing. Okay, so with a sentence like this, the first thing we would do is we remove all kind of formatting, for example, HTML. So here's what we would get, right? Just strip away all the tags. Oftentimes we have that. Another thing here, oftentimes when you get text, for us as human readers, it's very, very convenient to have something like Word or Google Docs. For a computer, that is not very helpful. So the best format for computers to work with text is really just the good old TXT format, like text in its most bare bones form without any nice formatting. Typically, then, we want to separate sentences into individual lines or individual instances, individual objects that we can analyze. There are tools that do this. We're going to see that later on. We then want to tokenize that. So when we write in English and in many Indo-European languages, we have things like clitics, like the v of I've. We have commas that we attach directly to the end of the word. And what we want to do in tokenization is we want to sort of insert white spaces to separate out each of these individual tokens into its own segment. Now, obviously, this differs. There are other languages that, for example, don't use white space to denominate the end of a word, where basically just by looking at the symbols, you can determine, oh, this is the end of this word, and here's the next word. You don't need a white space in between. So there, it's a slightly different task. Here, for the sake of simplicity, I'm going to use English as examples because I assume everybody is familiar with that. If you hear, obviously, if you work in a different language, and you should, there are, idiosyncrasies. There are things that are particular to that language that you need to account for. And luckily now there's a wide range of tools that work for languages other than English. The bulk of the word is oftentimes to normalize this. So we will typically lowercase everything unless, unless upper lowercase holds some information. But many times it doesn't for classification. So we're going to, typically lowercase all the text. We can use something called lemmatization or even stemming. Lemmatization means we will reduce words to their dictionary entry. So if you see the word going, you're not going to look up the word going in a dictionary, you're going to look up the word go, right? And so this is what we're doing when we do lemmatization. Stemming is an even more aggressive version of reducing words to their core by basically just chopping off things at the end, following a set of language-specific rules. And that would, reduce everything to its sort of atomic, irreducible core. So it would reduce constitute, constitution, constitutionalism, all to a root or a stem constitute without even the E. This makes it much harder to read, but it reduces the variation by quite a bit. Depending on what task you're interested in, it can be good to be very aggressive in reducing this variation. For example, for topic modeling could be useful. There's a bunch of words that we're not interested in typically. So these are called stop words. Typically, these are determiners like the and a, personal pronouns like my, your, ours, pronouns like us, we, you, she, it, and prepositions like in, of, before. Sometimes you will want those, for example, if you want to do author identification, because they're sort of like a fingerprint of every person. Everybody uses them in an idiosyncratic way. Sometimes, however, you will also want to remove words that are just super common in your particular domain. Let's say you're working with party manifestos. The party might very often say, we, the Freedom Party, or whatever they call themselves, will do X, right? And you can basically remove the name of the party because it's so frequent that it doesn't carry any information. You basically know which party the manifesto comes from, so you can safely ignore it. So in many cases, you might want to remove certain words. You can also remove words by their part of speech, POS. For example, you could say, oh, I'm only interested in nouns, verbs, and adjectives, maybe adverbs. Everything else you can throw out, right? So this is another way of reducing the variation. And then last but not least, what we would do is to join collocations. Collocations are words that usually occur together. So if you see one, you will also see the other. Examples here obviously are things like New York and Los Angeles, which happen to be written into tokens, into words, but in our heads, we don't even analyze them as two parts anymore, right? New York is not the new version of York. It's just one concept in our brains. And so if things occur together a lot of times, then we typically just join them to sort of distinguish that in the flowing text. We're just going to replace the space between them by an underscore, which also then makes them a single token. And so if we do this, we basically go from the text in its raw form that we've downloaded from the web to this very, very bare bones bag of words where it's might be a little bit harder for us as a human to read it, but for a classification task, we hopefully have distilled it to just the relevant elements that we need to sort of find out what class, what label we should put on this text. There's a question?
Yes, Manish asks, could you elaborate more on how reducing numbers down to zeros can help?
Yes, that's a very good question. So there are, by definition, an infinite number of numbers, right? Usually, for most intents and purposes, we're not interested whether somebody bought, I don't know, 3 CDs or 15 carrots or 2 houses, right? We're just interested in the fact that somebody bought a number of something, right? Unless, of course, you want to do financial analysis or something where the actual number matters. So rather than dealing with a potentially infinite number of numbers that we have to account for and that each become a feature in our input space, a dimension that we have to deal with, an independent variable, we will just collapse all of the numbers into 0. However, we will keep sort of their shape. So if you just replace every number with a 0, every digit with a 0, a 4-digit number is probably going to be a year, right? A 2-digit number might be an age. 2 digits followed by a dot or a comma followed by 2 digits is probably a price, right? So by simply reducing the digits to 0 but keeping their shape, we can maintain a lot of the relevant information, but we reduce some of this variation. So we reduce a potentially infinite vocabulary of numbers to, a manageable number of different number shapes. Does that make sense?
Can you hear me?
Yeah.
Okay. So yes, that makes sense, but I still had the question that exactly do you analyze whether the number would be important or not? Because you can manually do that, but you don't have like a foolproof technical way of doing that, or do you? That's the question.
Yeah, so good question. So in all of these things, the proof is in the pudding. We will see in machine learning, or in classification, what we're ultimately interested in is building a classifier that generalizes well to unseen text, right? So we're going to talk about performance. We want a classifier that gives us the correct answer with new data. So what we will do is we're going to hold out some data where we know the answer, and we're going to test the classifier on that. And we're going to say how much of that does the classifier get correctly, right? And one of the important iterations in arriving at the final best classifier is to try out these things, right? What happens if I just remove numbers altogether? Does that affect performance? If it doesn't affect performance, then sure, let's do it, right? If my performance drops, if I remove numbers altogether, then well, I won't do that. What happens if I instead reduce them to just zeros? Okay, that actually helps performance, right? So we're going to go through these iterations of performing different types of pre-processing and featureization of representing the text in different ways. And we're going to observe the effect that each of these decisions has on performance on our development set, until we're happy that we've made the right decisions. So the technical way to do it is to try different formulations of pre-processing, of featureization, of representation of models, and observe which one gives us the best performance on this held out data.
There is another example that Marco asked. Is this example specific for topic modeling? For sentiment analysis, you should keep didn't. How do you relate like with prefer in this example? And in the original sentence, they refer to the opposite sentiments.
So this example, so good question. We're going to talk about topic modeling tomorrow, if you tune in then. For topic modeling, we're going to do things slightly differently. In this case, we don't have to actually relate things to each other. And also, here I haven't shown any label. So, this might be an example of sentiment analysis. This might be an example of geolocation. This might be an example of, anything else. And depending on what your target is, what you want to learn to classify, some words might be more or less important, right? And it could be that one type of words that are very important for one task are completely irrelevant for another. For example, pronouns, right? Very important for author identification, probably not very important for sentiment analysis or geolocation. And the task here is to kind of like find out what you want to do. To some extent, you can be a little bit hands-off, and you can through this trial and error find out which of the steps help most. Obviously, in retrospect, it can be useful to understand why excluding, for example, verbs or another class is helpful, right? To explain and understand what's going on.
Thank you. There is another question through private message. What if the capitalizations is an important signal for the sentiment? For example, people write in angry capital letters, for example. So would lowercasing everything in this case reduce the predictive power of the model?
Very likely, yes. Yeah. So this is a good intuition. This is why I said, right, like your domain knowledge, the thing you already know or suspect about the domain, the thing you're working with, will help inform your decisions at this stage. And there's no one size fits all in pre-processing. This is a wonderful example, right? There's a lot of angry caps, all caps, right? Which will tell you something about the sentiment of a person, right? And so if you're doing that, removing caps, removing capitalization is probably going to be a bad idea, right? For other cases, let's say geolocation, capitalization probably doesn't matter at all, right? But this is something that you, as the designer of this algorithm, can bring into the process and say, well, I happen to know that people often use capitalization to express anger, so I'm going to leave that in. I'm not going to remove it. Yeah. So absolutely right intuition.
Thank you. That's all the questions so far.
All right. So I've shown you all of the possible steps that we can take here for pre-processing. Again, for the particular task you will work on in your daily life, in your line of work, you will have to choose the set of pre-processing steps that you want. Oftentimes now, people use representations of entire sentences or documents that are just, turned into a vector, and they don't do any pre-processing other than, splitting words up a little bit, which, sort of creates like a huge amount of variation and a relatively large vocabulary, but that then gets compressed into like a very low dimensional vector representation. So people use deep learning tools. There's a tool called BERT, which currently is dominating all of the high scores for all kinds of tasks in NLP, which basically takes a sentence or a document and turns it into a, let's say, 512 dimensional vector. And there you actually don't have to make these decisions. That's good for performance. That might not be actually great for having a better understanding of what's going on. And in my experience in social sciences, right, it's a wide field, right, hard to generalize. But oftentimes we also want to understand and explain later to others what has been going on. And so there, it can be good to know all the steps we've taken and be able to explain why we've chosen different decisions. So these researcher degrees of freedom become important. So yeah, in the end, I've shown you everything that is possible in terms of pre-processing. You could do nothing of it or all of it or something in between, and that something in between will probably depend on what it is you're working on. Okay. I've talked a little bit about joining these words together. So there are some words that are combinations, right? So if you look at these words, frying pan, social media, and thought, New York, and of the, these are all very frequent word combinations, but some of them you'd probably want to put together as like one concept, right? In a class, we would now, like have a discussion. This is going to be a little bit difficult online, but I guess most of you have already made up their mind. If you're anything like me, you'd probably think that frying pan, social media, and New York should really just be one concept, right? Whereas things like of the and thought are all frequent words, but they just happen to be next to each other, right? And, indeed, those words are called collocations, co-located, occurring together. These are basically single concepts. And there are statistical ways of finding these. You don't have to define them beforehand. What we're going to use is something called mutual informativity. So basically, what we're asking is, if I see one of these words, how likely am I to see the other? And if in 90% of the cases when I see one, I see the other, and vice versa, then that's probably a collocation. If I can see the word social, it's very, very, very likely to be followed by media or maybe club, but not too many other things. Whereas if I see the word and or the word the, they can be preceded or followed by almost anything, right? And we can use this intuition by basically in a corpus, in a data set that we're working with, we're computing the probabilities of this. Now, this might look a little bit complicated at first, but it's really, relatively simple. We're saying if I just reached into my corpus and I pulled out two words, what's the probability that I pull out these two words together, right? And then I'm going to divide that by the probability of like reaching into my corpus and pulling out a single word, and like how likely is it to be each of those individual words, right? And then because those numbers get relatively small, we're gonna, take the logarithm of it Logarithm is basically just, what you could call a squashing function. It's going to make, small numbers a little bit larger and large numbers a little bit smaller. So they're all in a, smaller range than originally. So, you have like a better sense, and you don't get like very frequent or infrequent words completely destroying the scale. We can do this, for example, here for Moby Dick. So we have a whole bunch of words. Turns out in Moby Dick, the terms Moby and Dick occur respectively 83 times. They occur together 82 times. So, if you noodle out the numbers, what you end up with is a PMI, a pointwise mutual information of 3.48. Basically, whenever we see one, we see the other, except for one case, right? So this is, we can safely say in this book, this is a collocation, right? Same with Captain Ahab, also relatively high pointwise information. It occurs usually together. There are some cases where he's just referred to as Ahab. So obviously those, kind of throw it off a little bit. And then there's things like white whale that are, similar to this, but somewhere in the middle. And then we go down to combinations like under the. Yes, both of those are frequent words, right? The occurs more than 14,000 times, but, only sometimes does it occur with under. And then, we go down to things like is a, which, is frequent, both individually and together, but it's not really a collocation. And simply by observing this PMI, we can draw a line through that at some point and just say, okay, everything above this line, we're going to, put together. Everything below that, that just happens to be words that stand next to each other. So here, maybe we would draw that line between white whale and under the. Obviously, there would be many, many more. Okay. So we have pre-processed our text. We have thrown out all
Dirk?
the words. Yes.
There's a question in the
Oh,
chat.
sorry, yes.
What does the CXY mean exactly?
Oh, yeah. Good question. So here the C is the count of, right? So in order to, probabilities are basically just counts that have been divided by some normalization factor. So here C of X is the number of individual words in Moby Dick. So there's 256,149 individual words in Moby Dick. And the count of XY is the count of a bigram, a combination of two words, obviously 256,148, one less because, it's combinations of two words. So we end up with one less than their individual words. And if we divide any one word by the total number of words, we get its probability.
Yes, there's another question from YouTube. And what is the threshold for a high PMI? Is it above 1?
Yeah, so typically you'd probably choose 1. Yeah. But you could sort of look at some examples and choose the threshold based on what you want. But 1 is generally a good threshold here. Yeah.
Yes, okay, thank you. I think that also answers DDO questions.
Mm-hmm.
That's it, yes.
All right, great. Good questions. So we pre-processed our text. We're going to go and do some classification with it. So let's say I open my email this morning and I get this email here, right? Take a few minutes just to look it over, look at the subject, look at the text. Just, based on a hunch, do you think this is spam or this is an actual email, right? I assume most of you, would immediately think, oh, this is spam, right? And now my question would be, why? Right? Like, what is it? You would be right. This is spam. This isn't an actual email. This is one I generated. But the question is, why do we have this intuition that this is spam, right? Well, it turns out there are individual words and combination of words that make it more likely that this is spam, right? If we see this, we're like, there's something that triggers in the back of our head that goes like, this doesn't look like a normal email. And in fact, the way I generated this email was I looked up some of the most frequent spam terms and then just put them together to form an email, a sentence, right? So all of these, right, combinations of words or individual words are essentially, you know, markers of spam emails. And what a classifier does is essentially the same thing, right? A classifier has a certain weight, a certain probability attached to each term or combination of words that says this is more or less likely to be spam if I see this, right? And we sort of do something similar in our head. And in fact, if we get an email like this and we click it and say, oh, this is spam, we have labeled it. And this is another thing we can do to then, you know, improve the classification of future examples. I think there was a question.
Yes, Gabriel asks if how would the methods of collocations be extended to more than 2 words? For example, international monetary funds. Do you build up the full words, like the first joint international underscore monetary, and then you do international monetary and then another underscore for fund?
Yeah, good question. You could do that. You can also compute the probability of trigrams and fourgrams. So a single word is typically called a unigram. 2 words together are called a bigram. 3 words a trigram. And then we don't call it a quadgram, although sometimes people do it, but it's typically 4-gram, 5-gram, 6-gram, and so on. You can collect the counts of those and then, you know, divide those by the other relevant counts and thereby get probabilities. I didn't go into this, but, you know, like probability wise, it's a fairly simple extension of that. And there are tools in the NLTK library that do that for you. And you can use bigrams or trigrams or even fourgrams to compute the PMI and a number of other measures for that. So yes, you can either do it for bigrams, and then, you know, if you have like several bigrams following each other that are all collocations, you would just like chunk them all together into one long collocation. Or you could say, okay, I'm going to run, you know, I'm going to compute the PMIs for bigrams, I'm going to compute the PMIs for trigrams, and I'm going to compute the PMI for fourgrams. And then I'm going to start, you know, first looking at all the fourgrams that are above 1, all the trigrams that are above 1, all the bigrams that are above 1. And, you know, they're basically, you know, simple extension of the probability computations that are involved in the PMI. So the basic equation stays the same. The way you compute the probabilities is, you know, slightly different, but again, basically count and divide to get the probability. And yeah, so that's typically how you would do it.
Thank you. Gabriella said that she's understood it very well.
Sorry?
Gabrielle said that she understood it. Thank you.
Okay, fantastic. Great. Good. So, oh yeah, so in the textbook that I have, and I think I also send around a link for like a draft version for teaching purposes, that there's like code to compute that. So you could basically copy paste that code to get the collocations. Okay, so yes, we sort of use our intuition, our sort of rough estimate of how likely the occurrence of a particular word in an email is to make it spam or not spam. All of these words could potentially also occur in a non-spam, in a ham email. But, you know, the more we see, the higher the likelihood becomes that this is actually spam. And the same happens with the classifier, right? This is exactly the same thing. Now, when we work with data, we're going to use matrices. Matrices essentially are just rows and columns of numbers. Like it's a big table that has a couple of, you know, special properties. Linear algebra, I mean, I'm simplifying linear algebra a lot here, but, you know, essentially you can think of it as a large table of numbers, where basically each row of that of that table is a particular instance, is one document, right? Maybe one email or one tweet or whatever the size of the document we're interested in is. And then we call that a row or feature vector, because each of the columns is one particular feature, one independent variable, one term that we're looking at. And so each individual cell here is going to be a number, a simple scalar number, typically a real valued number, could be negative, could be positive, but something like 0.35. And yeah, like each of the columns is basically one of the dimensions. And typically in the literature, and certainly throughout today, we're going to refer to this as X. There were more questions?
Yes, there were two more questions. So one's relating to the pre-processing step. Would it also make sense to somehow deal with acronyms in preparations? And they're thinking of New York as NYC or UN agencies, for example.
It's a good question. The sort of cop-out answer is it depends, right? It could be that, you know, by expanding those acronyms, known acronyms, you can sort of like reduce the variation. You can give your pre-processing a little bit more, you know, data to work with, a little more information, which would make it more likely to make New York City a collocation. But in that case, you kind of like expanded it to then have it reduced to a single item again as a collocation. So, you know, you're sort of like doing and undoing the same process. But, you know, it could be useful because it might add other amounts of information. Yeah, it's a good idea.
Yes, thank you. And another question is, can you build a spam filter breaker by knowing all these lists of spam terms and avoid them altogether in constructing a new spam email?
Who asked this? This is a bot.
Service, I think.
I mean, so right now we have these language generation tools like GPT-2, GPT-3 by OpenAI that basically generate very, very real looking text, right? And you can play around with it on the internet. It, you know, can generate text that looks absolutely like it was written by a human. It's very coherent, kind of sensible, almost indistinguishable from you know, human written text. So, you know, it is by now possible to generate text that would probably pass a spam filter. This is also why, you know, whenever you click on a new email, like the spam emails we get today look different from the spam emails we got 20, 30 years ago. Spam classification being one of the first successes of machine learning and of classifiers. Every time you know, mark a new email as spam, you're basically updating those tools. You're giving them more to work with, more understanding of how things work. And you know, right now we're just talking about the occurrence of words, but there might also be sort of more higher level concepts, right? The general topic of an email, or sort of the tone in which it is written, but also meta features like, is this sender in your general communication? Like, have you interacted with this person before? Was it written from an IP that, you know, has sent out a bunch of different things under different email addresses, things like that. So it's not just individual words, and, you know, these tools can learn to, you know, take more things into account. But yes, by now it is possible to generate text that, you know, is completely nonsensical and could be spam, that doesn't contain any of the words I've shown, right? So it's a little bit of an arms race between like spam emails and detection. Yeah.
Okay, thank you very much.
Okay. So the reason we're talking about these matrices is that, you know, once we have a matrix, we can do linear algebra with it. Fantastic, right? You came here, you didn't expect it, and bam, I'm talking about linear algebra. In fact, a lot of machine learning under the hood is nothing else but probability theory and linear algebra, multiplying vectors and matrices together. In fact, I would like to have a tool in a browser that replaces the terms AI, ML, NLP with linear algebra every time they occur, which would look a lot less fancy, but it would be a lot more accurate. Basically, what we're doing is we're going to multiply matrices together. And that is essentially what we do in, for example, logistic regression to get our answer. We're going to look at that in a second. So what we need to do is we need to get our text into such a matrix, right? Where each row is one text, let's say a tweet, and each column corresponds to, for example, a word in the text, right? How do we do that? That's the first part of representations. The most straightforward and simplest way and most explainable way is discrete representations. And what we're going to use is something called bag of words. So my wife is also an academic. She works in a different field. The first time she read a paper from my field, she said, like, are you guys serious? Like, what are you talking about? What is a bag of words? Is this like, do you actually think it's a bag? And yes, it's a bit of a weird term. Basically, what it denotes is that you have a collection of words that are unordered, right? So where they occurred in the document and in which order doesn't matter anymore. It's essentially like you took a page. Imagine like one of these old things that have been used by printers in order to, set a page, right? They would put all the words in there as little lead types. And then when you're done, you can just take that whole row and like dump it out into a bag. And, you wouldn't know which word came from where, but you would have like all the words in the bag. This is sort of a little bit how we approach things in discrete representations. Basically, we're taking a document. We would go through, we would say, okay, what are all the words that are in there? And then we're going to say, how often have we seen each word, right? So just going to go through. We're going to collect a count for each word. You could use a counter object in Python. Very easy, right? And then essentially what we're going to do is we're going to say, assign each of these words a column in the matrix. So if we have, 7,000 words, then we're going to have a 7,000 dimensional vector. And then we're going to represent this particular document as a 7,000 dimensional vector, where we just put the count of each word in the column that corresponds to that particular word. Now, if you do that, not every word occurs in every document, luckily. Especially if we have very short documents like tweets. So as a consequence, a lot of these columns would be empty, right? The count would be 0. We haven't seen the particular word in that particular document. For example, here, we haven't seen the word beer in this particular document. So that column, the value in that dimension would be 0, right? Also note that while we know how oftentimes the word Shakespeare has occurred in this document, we don't know where it occurred in the document, right? So this is why it's a bag of words. It doesn't preserve order or position anymore. So there was another question.
Yes, it's also questions from a previous part of the lectures. Are stemming and lemmatization, keyword normalization techniques in NLP?
Yes. Yeah. So those are ways to normalize the text and like reduce some of the variation. In linguistics, this is called the inflection, right? So in English, inflection is very simple, right? You have go, and then you have the third person singular S, he, she, it goes, right? But you also have things like the gerund going, and then you have typically like past tense ending. In other languages, right, Italian, for example, has a much richer inflection paradigm for each verb. And basically you want to sort of reduce that because you say, well, I'm not interested in the tense, like whether this happens in the past or the future, or whether it's done by one person or two or several or you or me. I just am interested in the fact that this action occurred. So, yeah.
Thank you.
All right. So this goes back actually neatly to pre-processing and to stemming. So imagine, in this process of like collecting the vocabulary and then creating a matrix that has one column for each word in our vocabulary. What if we don't normalize? What if we just have one column for each possible word, right? So the number of words in a language, this is a very tricky question. Yeah, sounds very simple, is very tricky, depends on what a word is. It depends on what your definition of is, as Bill Clinton famously said. So, is New York 2 words or 1 word, right? Depends on who you ask, right? Do you count all the different forms of to go as different words, or is that all just 1 word? Going, goes, went, all just 1 word. Depending on how you count, you arrive at tens of thousands to hundreds of thousands of words. Do you count names? Like, is Twitter a word, or is it just a name? Do you count numbers? But easily we would get 100,000, maybe even 500,000. But most of those words will occur once and then never again, right? So that would make it like a very inefficient way of representing text, because we'd have like a very, very long vector for each document, but that's overwhelmingly zeros because we haven't seen each word in each document. And so this is why this pre-processing and reducing the size of the vocabulary and the variation is so important. All right. So this goes back to this man here, who was named Zipf, I think George Zipf, who observed that in almost any language and in any part of language, there was this weird distribution. There are some words, there are some sounds, there are some morphemes, parts of words that are super, super frequent, right? That occur over and over and over again. In English, for example, the term the. And then there are a whole lot of words that you see once, even in a large collection of words, like a huge corpus of books. You see this word maybe once, right? Like, think about how often you've seen the word the. Now think about how often you've seen the word platypus, right? The will be all the way to the left of this graph. This is a power law distribution. And platypus, in other words like that, will be all the way to the right of this distribution, right? And this holds for basically any corpus, any language. It holds for words, it holds for sounds, it holds for letters. They all follow this distribution. So this is typically called in linguistics a zip distribution. You could also call it a Pareto distribution or a power law distribution. But basically it means there are some things that are super frequent. The next frequent thing is going to be, half as frequent or a third as frequent. The next thing is going to be half as frequent again, and so on and so forth. And like, whether it's half or a third, that is the factor that, determines and defines this distribution. Interestingly enough, most words in a language fall to the left of this line. So you only need about 200 to 500 words to basically account for 50% of all the word occurrences that you will see in, say, a newspaper. Is this going to be helpful? Well, no, because the things that are in those 50% that are super frequent are things like determiners, the, a, and pronouns, right? You, me, she, him, they, and other things. Those are good words to have, right? And we need them to form a grammatically correct sentence, but they usually don't convey a lot of information. So a lot of the information is in those other words, right? So if I tell you, I saw a platypus, right? I can ignore I and I can remember saw and platypus, and that actually, captures the information. But both of those words will be to the right of this line, right? We're going to get back to that. First, I wanted to briefly, again, define this term n-grams that we talked about before. Very simple. Here, famous sentence from Franz Kafka, The Transformation. N-grams are sort of the unit of analysis. So unigrams or 1 grams are basically the individual tokens, the individual words that we have in our text symbol. Bigrams are combinations of it. So essentially we're dragging a 2-word window over this text and photographing each combination of words. Those are bigrams. Trigrams, any combination of 3 words. 4 grams, not quadgrams, combination of 4, and so on and so forth, right? Why am I talking about this? Well, because we will use this to compute pointwise mutual information, but also to compute a weighting factor. Because some words are more interesting than others, right? If I have a bunch of texts, there will be some words that are very, very interesting, like sustainable. Maybe if I'm looking at quarterly reports of companies, the fact that they're mentioning sustainable in one but not another quarterly report is going to be interesting for environmental purposes, whatever. The fact that they use the word "the" is basically irrelevant, right? They have to use the word "the." I can essentially ignore any occurrence of the word "the." Now, you and I know that, but how do we tell the computer this, right? Somehow we'd want to attach a weight, a very low weight to a frequent word like "the," and a higher word to a more informative, interesting word like "sustainable." And this was a problem in the early days of information retrieval, of working with the web, right? And like of representing this. We have to thank Karen Sperrick-Jones for the invention of this weighting scheme. She was one of the pioneers in information retrieval, and a lot of the work she did essentially, enabled where we are now. She actually almost became a teacher, but then got bored with teaching and then decided to go into computer science. She is behind, a lot of the things that we use now every day that you have been using since you've gotten up, and that, I've been using to make this presentation. She was also a huge champion of more women in computer science. Still, a difficult topic, not very well represented in computer science, unfortunately. And she's also the namesake of a prestigious computer science prize. So if you meet somebody who has a Karen Sperrick-Jones prize to their name, they're a smart cookie. So thanks, Karen. Anyway, back to this issue, right? A lot of words have this weird frequency distribution. So just the frequency of a word alone doesn't help us, right? There are all these frequent words to the left of this curve that basically don't say anything, right? There are a lot of, words to the right that are interesting, informative, and juicy that we want, but, they're not very frequent. So frequency alone isn't it, right? So we somehow want to focus on that right, the just right, the Goldilocks region of this, right? And yes, of course, George Ziff could have told us that before. So how do we find this informative region of the distribution? Well, Karen Sperrick-Jones' intuition was that we can basically look at our data matrix. Remember, each column of this matrix is a particular term, and we can look at the values in there. So here, let's say we have the term sustainable, right? And it occurs in those 4 blue marked documents. In the one, it occurs twice. In another one, it occurs 5 times. And then there's 2 where it occurs once each, right? So we can talk about statistics of this word in 2 ways. One, we can say in our corpus, in our collection of documents, we have seen this word, this term 9 times, right? In total. So this tells us something about the position on this curve, the zip curve, right? But we can also look at it and can say this occurs in 4 different documents, right? And that is, a different way of assessing how frequent a word is. So we have the term frequency, how often do we see this word, and the document frequency, in how many different documents does it occur. Now, we can use the inverse document frequency, which is defined like this. We take the number of terms, we divide by the number of documents we've seen the word in, we take the log of that to account for outliers and to squash everything a little bit. But it turns out if we take the term frequency of a word and we divide it by the number of documents that it has occurred in, then we actually get a distribution that emphasizes the interesting region much more than the uninteresting one, right? Because every word that's very far to the left will have a very high term frequency, but it will also have a very high document frequency. The word the occurs a lot, but it also occurs in almost, or definitely probably in every document that we have, right? So if we simply kind of divide the number of times we've seen the by the number of documents it occurs in, it becomes a very small number. So we downweigh it. However, the word platypus, maybe it occurs only 9 times, but in 4 different documents. So 9 divided by 4, right? So we get 2.25 essentially. So that indicates that platypus is a much more interesting word than the. People talk about the burstiness of words. So if a word occurs in a document several times and then not anywhere else, that is a bursty word, right? It bursts into being in one document. And that makes it probably, interesting. So basically, we're going to take how often we saw the word and divide it roughly by the number of documents. And this is TF-IDF, and this basically brings out a lot of the information in the documents. We can plot this, for example, again, here I've used Moby Dick, basically because it's freely available on Project Gutenberg as a text document, and we can plot the inverse document frequency by the TF-IDF value of a word, and we can sort of weigh that by the term frequency, so by how frequent a word is. And if we do that, we see that, like the most interesting words to the lower right are kind of the words like the old-timey form of you, chapter, which occurs very frequently, and then also, Ahab, man, this is a book about metaphysics and about being and whatnot, but also about whales. It's a book about whales. Sorry, spoiler alert. And you could sort of plot these things and then see how this shakes out. All right. My suggestion would be to take a quick 5-minute break here and then go back to something else. Is that okay with everybody?
Yeah, everyone is thumping up. So
okay, great. All right. So then we take a quick break here, and then we're going to repeat because I think we've already gone. Yeah, we're almost at the 1.5 hour mark, and that typically is when concentration flags a little bit. So let's take a quick 5-minute break here, and then we're going to go back and return with the next steps of what to do. All right, see you in a bit. Hello, everybody, and we're back again. Let's take a few seconds so everybody can get back in learning mode. Hope you had a bit of time to let everything settle down a little bit in your brain. Don't worry, this is a lot of new material probably for everybody. If not everything makes sense on first try, that is expected, that is normal. In fact, I'd be very surprised if all of this made sense at the first time. A lot of these things you have to see or hear 2 or 3 times. Obviously, I'm going to share the slides. Later on, we're also going to see everything in action, and then maybe it makes a little more sense when you see how it's applied, and then you can also read the book or the lecture notes and sort of get a sense, get a third way of looking at it. Depends on which way you most easily learn, whether you're a visual type or abstract type. So don't worry if some things right now seem a little bit confusing. I promise they will make sense eventually. Okay, let's start back up. So where are we? Okay, we want to build a classifier, for example, to determine whether a message we received is spam or not. So what do we need? Okay, we need to take the text of the message. We need to remove unnecessary words and material. So we do the pre-processing, and then we need to get this pre-processed text into a matrix of sorts, because ultimately what we want to do is linear algebra, right? We want to multiply that matrix with a weight vector, and then as the output is going to be the label, so the probability that something has a label. So how do we get this pre-processed text into a big data matrix X? One way is represent each document as the counts of words, maybe in order to increase the informativeness, the sort of the focus more on the really juicy, bursty, interesting words. We can not use the raw counts of the words. We can actually use the TF-IDF weights of the words, and that will sort of focus us on more informative, more interesting words, and that will help with classification. So that is one way, right, to get from our pre-processed text to our data matrix. There's another way, and this way has become increasingly popular over the last few years because it is more powerful. It can sort of capture more of the underlying meaning and connections between words than the count-based discrete vectors can. And this is called dense or distributed representations. Now, the intuition behind this is that words by themselves don't mean necessarily something. They mean something because they occur with other words. And whenever you talk about word embeddings or distributed, meaning you kind of like contractually obliged to quote Firth here with "you shall know the meaning of a word by the company it keeps." So rather than representing a document or an individual word as counts over characters or over words or something, maybe we can just have this big space in which we put similar words close together as like a cluster. And then we have these clusters of words in the space as little clouds of words together. And the position of each word with respect to all other words will capture its meaning in some way. And that would be really nice because it would, capture meaning much better than just some boring kind of like, counts over how often we've seen a word in a document and weighing that. So this is actually, an old concept, latent semantic indexing. For example, if you wanted to move to Copenhagen and you were looking for flats in Copenhagen on a search website of your choice, right? You might use the English term flats, British English term flats. You would get results that contain that, but you would also get, results for things like apartments, which is a synonym or another term. You might even get, housing or other things. So clearly these words mean similar things, mean the same thing even. And we want to capture this similarity, this in meaning together, right? Maybe we also want to capture that, things like vaccination and syringe and jab and hospital oftentimes occur together. They form like a semantic field. Because if we can do that, and we can, give this information to our classifier, they might be able to make more sense. We talked about, breaking the spam classifier by using words that are not in there. Yes, you could, use words that are not captured, but, you wouldn't sort of escape the meaning or the semantic field of spamminess. And so a method that sort of made a big splash in 2013, this goes back, to the 1990s when people had like approximations of this idea, where they basically said, let's build this concept into the way we represent words, and we then in extension represent documents. So what we want is a way to represent flats such that it's similar to apartments, and we want to represent that as a vector. So a series of numbers, a list of numbers essentially, that describes where the word is in a space, and we want these two words to be close together in space. So, whoops, these are weirdly labeled axes. Never mind. Basically, what we want to say is we have this two-dimensional space, and flats and apartments should be, relatively close together in this space. We can represent a vector as a point in space by drawing a line from the origin, 0, 0, to that word. And then we can describe the similarity between these words as the angle between those lines from the origin to the point in space where that word lives. And so we would see that flats and apartments are close together. They have a very small angle. And words like flats and platypus are, much further apart. So how do we get this? Well, we can describe each word by its coordinates in this two-dimensional space. For example, we could say that the word flats is represented by the vector 16.3 and 7.8. That's its locations. That's where it lives. And, other words would get other vectors. Now, if we have a word represented as a vector, we can compute the similarity, the cosine similarity, by basically taking the dot product of the two words and then dividing sort of by the joint length of each of these lines. And essentially, what we would get is this pink angle between the words. If this is a very high number, then that means the words are very, very similar. If this is a very low number, that means those words are pretty far apart in this space. And that should somehow correspond to the meaning of those words. It could even be negative, which would mean these two words basically never, are completely unrelated to each other. Yes, there's a question.
Yes, there's a question. Why do you use the angle cosine distance instead of the Euclidean distance?
This is a type of, or this is a Euclidean space. You could also use the Euclidean distance. There are other definitions. Cosine similarity is kind of the one. There's also things like Jacquard distance. The cosine similarity is the one that has become most standard. There's a couple of properties that just make it nice to work with, like it's bounded by -1 to +1, and so it corresponds a little bit to opposites versus similarities. But it's largely probably convention, I would say.
There is another question. Sorry, could you explain again how you get the vectors for each word before calculating the similarity?
Excellent observation. And yes, I haven't explained that yet, because this is the big question, right? Like, how do we get the word flats to a point where it's close to apartments but far away from platypus, right? And this is the sort of the magic behind, well, not magic, it's again linear algebra. It's always linear algebra. This is sort of where we want to get. Yes, exactly. How do we get this space, this configuration of words in this space that captures the fact that some words are similar and others are not, right? Oh, right. This is just as a background. Dot product. I'm not sure, like everybody's familiar with it. Essentially, you take two vectors and first you multiply each dimension together. So here 0.5 times 2 is 1, 0.5 times 6 is 3, and then you sum everything up like so. And so this would be the dot product between the two vectors here. The vector norm is essentially the length of a vector. What you do is you remove any negative number by squaring it and then taking the square root of the whole thing, and then you basically sum together all of these numbers. So here the vector norm, the length of this vector would be 6.324. But yes, this doesn't answer the question, how do we get to this space? We're going to get there in a second. Once we have everything in this space, we can also do things like, nearest neighbors. We can say for a word, like the gray one that is surrounded by pink here, with the circle around it. We can say, what are the 5 nearest neighbors? What are the 3 nearest neighbors? And we can use these similarity measures to get that. And again, they should correspond to meaning, right? The wider we make this neighborhood, the broader the semantic fields become. And yes, how do we get the words into position? Well, let's think about a big fridge, and you have little magnets that you put on that fridge, right? Basically, in the beginning, you put all the words randomly on the fridge, and then you just pick random pairs of words, and you say, have I ever seen these 2 words in the same sentence? If yes, then let's move them closer together. If not, let's move them further apart, right? And now, if I do this over and over and over and over and over again for all the different pairs of words, I essentially arrive at a stable configuration. So obviously, in the beginning, if I move 2 words further apart from each other, I've also moved them further away from other words that they should be close to. So, there's like chain effects and ramifications for every move we make. But in the end, we arrive at some way, shape, or form that sort of puts words that have occurred in the same sentence closer together and words that never occurred together further apart, right? We could even weigh it by how often we've seen them together, and that determines how far we move it. But essentially, by repeating this again and again and again, we sort of structure this space. And because of this intuition by Firth, that the meaning of a word is determined by the other words that are around it. And we have incorporated this into our algorithm here by saying, has it occurred in the same sentence? We sort of structure this space. We structure the distance between words and groups of words by their semantic similarity, by their probability of occurring in the same context. Now, you need to chew on this a little bit and let it sink in. But essentially, by incorporating this objective function into this algorithm, it sort of captures the meaning of words with respect to each other. I don't know, was there another question about this?
There is an additional question. Seen in the same sentence doesn't mean seen together in one sentence, right?
Yeah, so I say sentence here. The way it's implemented in the document, in the algorithm, is it says within a certain window of words, right? So have these two words occurred within, let's say, 10 tokens of each other to the left or to the right. That's how it's implemented in reality. But you could think of it as like, has it occurred in the same sentence?
We also have a hand.
Yeah.
Gabriella,
Yes. No, my
speak.
question was about this sentence thing. I was going to ask if you're relying on punctuation, but I think you just answered the question. You're just basically using a window, right? Okay.
Yeah, exactly. So by using this window distance, you're no longer dependent on the sentence boundaries, right?
Yeah.
And so if you make this window very large, right? Let's say you make this window 1,000 words to either side, right? Then you would capture whether you've seen these two words ever in the same document, right? Whereas if you make it very short, let's say 3 words to either side, then you really make it, very, very narrow, and you sort of focus more on the syntactic properties of a word. The wider you make it, the more you focus on the meaning and the semantic or pragmatic use of the word. The smaller you make it, you really focus more on the localized syntactic meaning of the word. Mm-hmm.
We have a couple more questions. One is, I guess, like a follow-up on the previous questions about sentences. Why would synonyms be together in a sentence?
Mm-hmm. Yeah, good question. They are not necessarily together in a sentence, but what happens is that because they occur in the same sentences as other words, they are sort of pushed to a similar situation. So even though they together haven't occurred in the same sentence necessarily, they have occurred with probably roughly the same frequency to all the other words in those same sentences. So because this is kind of like a recursive process, these mutual distances stack up in the end to kind of structure this space in a way that similar words end up in the same space because they have the same distances to all the other words without necessarily occurring together. Yeah.
Okay, another question is a quotation marks if in same sentence. I guess it's like referring to something you have on the slide, right? Can this piggyback on earlier learnings, or we have to calculate it afresh?
Yeah, so the way this is implemented is that you give it a large corpus of texts, and then you collect these statistics first, and then you run this algorithm on it. The way it is actually implemented is much more, I don't want to say hacky, but it uses a lot of engineering tricks to make this basic idea happen. So this is the intuition. This is not the actual, you could kind of implement this as an algorithm, but it wouldn't be as efficient and wouldn't work as well as the actual algorithm, which sort of, implements this intuition in a much more engineering way. Yeah.
Okay, we have a couple more questions. Yeah. Couple from YouTube. We're talking about a high dimensional vector space, however, not 2-dimensional, right?
Yes, absolutely. So this is a great question. I was going to, get into this. So on a fridge, we have 2 dimensions, right? Up, down, or left, right. And that gives us not too many ways in which we can arrange that space, right? If, however, you use, in a 2-dimensional space, and you have these 3 words, if I move these 2 words closer together, I've moved this word here further away from this word, right? However, in a three-dimensional space, I can, stay in one axis and move it in that axis, keeping the same distance to one word, but moving it with respect to another word. And if I take 300 dimensions, I have a lot more degrees of freedom, literally, to arrange words with respect to each other, but remain at the same distance from other words. So yeah, like we're talking about a 300-dimensional fridge here.
Okay, another question also from YouTube. How do you find the optimal window of words? Is it just an iterative process?
Yes, this is a great question. So a little bit like going back to what I said before, it depends kind of what you want to capture. If you have a very small window, the algorithm will capture sort of positional syntactic similarity more, or that will dominate sort of how the space is structured. Whereas if you use a very large window, it will be structured more by general semantics, by meaning, by the general semantic fields that are in there. At the end of the day, yes, this is a parameter you can and have to choose for your data set. And it also depends a little bit on the size of your data, on the domain that you're working in, right? If you work with tweets, there's not really any sense in having like a window size of 200 because, that's longer than a tweet is going to be in words. Whereas if you work with party manifestos, larger window sizes might make sense, right? So this is a parameter that you can and have to choose.
Okay, and a couple more in the chat here. One from Michelle. Is there a reason we don't use semantic differentials, Osgood's work, I think she refers to define our semantic space?
I don't know what semantic differentials are, or I don't know Osgood's work. I don't know who that is. So
yeah, sorry, if Michelle wants to clarify that in the chat, we can address this question later then. And another question from Marcus. So the vector of a word only depends on the corpus it was trained on and is constant afterwards. For instance, a vector of a word doesn't change when it is used in a different context in my own corpus.
Yeah. Yes, absolutely. So the data you train this on determines, right, the connection. So in the extreme, let's say you train this only on tweets, right? You will have a certain structure of the space. It will be very different from if you trained it on cooking recipes, right? Or let's say if you train something on cooking recipes versus computer manuals, the word apple, would have like very different neighborhoods depending on what corpus you trained it on. These algorithms can be used by you. You can run them on your own corpus, and they're actually pretty fast now. There are, however, also pre-trained word embeddings that have been trained by large companies. So there are examples by Facebook and by others, by Google, and like also by research groups that have trained on large crawls of basically the entire available web. And so they should be much more generalizable. Sometimes you'd want that. You want like the most general definition of a word. Sometimes you might be interested in just how is the semantic space of my corpus structured. Maybe you work with I don't know, like a collection of UN speeches, right? And you are interested in how things are structured there and change over time or something like that. So in that case, you don't want like the general meaning of words. You want the meaning of the words in your particular context. But yeah, the choice of corpus that this is based on has an effect on the way this is structured. Also, maybe good to know, because we start out randomly in this space and we let it run, it will eventually sort of coalesce into like one stable configuration. But if we run this 2, 3, 5, 10 times, those stable configurations might look very differently depending on where we started, right? So they will be inherently consistent in themselves, but they might not be the same as another run where you started out differently.
Yeah, thanks so much, Dirk. We don't have any more questions as of now. Yeah.
Okay, fantastic. Very good questions. Okay, I don't want to belabor the point too long. These algorithms are basically can be implemented in different ways. You can basically check whether two words occur together, and it's like a classification task in itself, right? So we're using classification to learn these representations. And if it's wrong, then you change the input representations. Or you can do it the other way around. You can say, do I have an input word, and have I seen this? What are the output? What are the context words that I've seen this with? This is called the skipgram model. These are sort of, minute differences that probably will not matter too much to you. I just wanted to mention here, the way this is implemented, again, is different from the intuition I've given. For what we want to talk about today, this is less relevant. I just wanted to, tell you that this exists. And again, if you're interested, there's a lot more about it in the book. And there, by the way, there are by now fantastic YouTube videos, Medium articles, notebooks, tutorials on the web that really go into all facets of this. There are explainer articles that go through all the nitty-gritty math and all the details of the algorithm. So if you want to dive into this, there's a whole world of Word2Vec waiting for you. So one of the interesting things that they showed in this original paper by Mikolov et al. Was that you can do vector space semantics, right? So you have these you end up with the space where words are in this space by sorted or arranged by their meaning, but you can take the vector for king, you can subtract the vector for man, you can add the vector for woman, and then you end up in a region of the space where the nearest actual vector is the vector for queen. And so people showed that this works for all kinds of things. You can learn sort of the capitals of different cities. So Berlin minus Germany plus Italy is basically Rome, or minus Germany plus Russia would be Moscow, or all kinds of things. So this captures more underlying meaning than we would a priori define. There is a bit of a problem with antonyms, so words that are the exact opposite. So his kitchen was always could be dirty or could be clean. They occur in pretty much the same contexts, but they have opposite meanings. There are also other issues that come more and more to the forefront because you train this on large amounts of text. These vectors pick up on our, as a society, use of language and how we talk about things in the real world. That includes how we talk about gender, how we talk about ethnicity, how we talk about a lot of things. And there are a lot of really, really interesting works that have shown that we can use these embeddings as diagnostic tools to see how societal attitudes have changed over time, for example, with respect to gender roles, jobs that are held by different genders, or biases and stereotypes about ethnic groups. So these vectors, these representations do capture all of these things, right? Because that's how we as humans, as societies, talk about them. That does mean, however, that they also contain some of these biases and, introduce them to the classification task that we work with. So this is something we need to be aware of. And luckily, right now, there's a very robust and open and ongoing discussion about the ethics of natural language processing, of these tools. I myself have contributed to these things, written a couple of overview articles and things like that. But this is, not a resolved issue. And I think it's good to mention and to be aware that these things do capture things that we might not be aware of, and some of those things that we might not want in that way, shape, or form. But they can, on the flip side, also be used as diagnostic tools to give us a sense of how societal attitudes, are or change over time. Now, in the interest of time, I want to, go a little bit faster over this second part. The same idea, the same algorithm essentially can be used for entire documents rather than words. So similar documents can be represented. So here, for example, we ran this on the Billboard 100 historical collection. And you can basically see if you plot the position of country songs versus hip hop songs in a three-dimensional space, they essentially don't overlap, right? Which is not super surprising, but just based on the lyrics, you can see these are very, very distinct genres. In another work, we basically learned representations for different cities based on chat conversations that happened in those cities. And you can basically see that this essentially recreates the dialect continuum in the German-speaking area in Europe, with Switzerland, being very separate because it being very, very dissimilar to any of the other regional dialects. Again, same idea. The only thing we change really from Word to Vec is that we add the document labels as new words. So here, if we talk about cities, right, we place the words as before on our fridge, and we also add like special magnets, which are the labels of the documents, in this case, for example, cities, and then we move these things around. For each word and each city, we say, have we seen this word used in this document in this city? If yes, move them closer. If not, move them further apart. And essentially, what we end up with is a similar space. Again, this is how the model is set up. Implements this intuition in an engineering efficient way. But it gives us sort of nice, interesting results. For example, for these, words and cities, we can see that in the end, the vector for Vienna, the city, is close to dialect words from Vienna and also to some, like places in the city. So this,
Dirk,
yeah.
Sorry, we have one question on YouTube. Can you point us towards literature that discusses NLP as societal diagnostic tool?
Yes, absolutely. So computational social science as a whole has, a whole subsection where NLP tools are used to answer social science questions. There was the other approaches like network-based approaches and other things. A good starting point is the paper by Garg et al. 100 years of stereotypes captured in word embeddings, or word embeddings capture 100 years of stereotypes, or something like that, which describes in detail, it's a wonderful paper. It explains very detailed how using a corpus of books over 100 years, you can sort of learn societal attitudes towards gender roles and particular jobs, right? So plumber, is it closer to man or woman or whatever in 1910 than it is in 1990? And you can sort of see how things change over time. You can also see there's another paper by Kulkarni et al. From 2015 where they show how the meaning of word changes over the decades, right? You can see how the word gay starts out as like a synonym of happy, then sort of becomes kind of like a slur, and then becomes more associated with parade and pride, and then sort of like it changes its meaning, and you can see that reflected in its similar in the nearest neighbors that it has in a given decade in these semantic spaces. So those two papers would be good starting points. There's also a recent paper by Kozlowski et al., The Geography of Culture, I think it's called. It's from 2020, I believe, that use these techniques. And there are a lot more. A lot of societal information, sociocultural information is captured in language, right? And so using these automated tools, we can, leverage large amounts of data that are around to, analyze changes, but also to, structure and explore that space. When we talk about topic models tomorrow, if you tune in, that obviously is another and very popular way of exploring large amounts of texts and getting insights into societal dynamics. In the break, I can post links to those papers if you remind me, if I forget.
Thank you.
Okay, so there are these two types. Okay, so this has been a long journey. We have pre-processed our text. Now we want to transform it into a matrix. We can either do this with count-based vectors or with these distributed vectors where we just say, okay, I want 300 dimensions, and you just arrange things in those 300 dimensions that similar words or similar documents mean similar things. They are different along a number of different axes, right? So in the case of discrete, we can understand what each dimension, what each column means. Each column stands for a particular term in our data. In the case of distributed representations, word embeddings, document embeddings, dimension 15 doesn't mean anything, right? It is just one axis in this high dimensional space, and we can only interpret words or documents holistically through their distance from everything else. But in terms of classification, distributed representation oftentimes are more performant. They capture more things, and they are slightly less, I don't want to say biased because they have their own biases, but we don't have to make a decision about what we count and what we don't count, right? Because this is sort of built into the objective function of the algorithm. So it's more emerging properties, whereas in the case of discrete, where we have to choose what are the columns of our matrix, we sort of have more of a thumb on the scale as to like what we capture and what we don't capture. There are pros and cons to each of them, and again, it depends a little bit on the task you're interested in to see, what you want to use and what the better choice is. If you're interested in performance, distributed performance and only performance, you want good classification, then distributed is the way to go. Lately, there have been these neural network-based representations of entire documents where words don't always have the same representation. So the word apple might have a different representation in one sentence if it's about computers versus if it's about cooking recipes. So they're no longer just one size fits all. They are much, much more expressive. The algorithms to train them are super complex, and it's impossible almost to run them yourselves. You have to rely on like pre-trained models that people are now releasing, both research groups and industrial labs. But they do capture a lot more fine-grained information. On the other hand, yes, they can be used as diagnostic tools for societal attitudes and changes, but they are very hard to create causal explanations and post hoc understandings. So this is also why it says here, right, like distributed is more empiricism. We're interested in good results where we don't care why we get them, being crude about it, versus rationalism. We're not as much interested in that it works, but we want that it works, but we want to understand how it works, right? So we want a model that we can look at and understand versus a model that, works whether we understand it or not. So those are the two different ways in which we can, take our text and transform it into a big matrix where each row of the matrix represents a document and each column is a dimension which either corresponds to a term or is just one dimension in our high dimensional space that, defines the relation of words or documents to each other. Okay. So that gets us finally to the part where we can actually stick this thing into a classifier and then learn how to classify things. Looking at the clock, it's 5 minutes to 12. I think this would be a logical point to take the slightly longer, the 15-minute break now, because then we're going to, start looking into how to apply these things. We've now gotten to the point where we sort of, we have the matrix, we've taken our text, we've pre-processed it, we've turned it into a matrix in some way, shape, or form. Now we can do the classification. Maybe let's take a break now. My suggestion would be we spend more time on this background, and then if we have slightly less time to work through the Colab notebook together, we will get there and we will go through it. But that Colab notebook to some extent is self-explanatory. So if we don't get through it together, you will be able to go through it yourself and like see and understand what's going on there. But that presupposes that we sort of like laid the groundwork theoretically. So I would say let's take a break now. After the break, let's not directly go to the notebook, but let's take our time and like really finish this section. So, we all start out the notebook with the necessary, foundation. Does that sound good to everybody?
Yes, perfect.
Wonderful. Any questions before we go into the break?
There's just one question popped up right now regarding the choice of software. We will only use Python today and tomorrow, right? Would you recommend to learn Python for NLP instead of trying to do everything in R?
Yes, absolutely. R is a wonderful language. It can do a lot of things, but it was not designed to work with language. It can work with language, and there are things now. And obviously, if you're fluent in R, this will be an easier starting point. Python is a much more all-purpose programming language. It has a huge support for natural language processing. It is the language of choice for research and development in machine learning, in NLP. So if you want to go beyond certain kind of pre-packaged things, then absolutely, I would highly recommend learning Python. The good news is if you already know R, switching to Python is kind of like knowing one Romance language and then learning another one. So if you know French, it's a little bit easier to learn Spanish and then maybe Italian. So, you just have to, super simplifying everything here. You mainly have to learn new vocabulary. So instead of saying X, you use Y, and the structure is a little bit different, but you understand the underlying concepts. But yes, so R is great for a lot of things. Again, for text, it's probably not the first choice because that's not what it was designed for. Whereas, Python has a lot of native support. And I think it would be easy for you to probably switch. I've seen a lot of people in my classes and PhD courses that know R or Stata or, in some other programming language that's more specialized and more statistics-based, successfully switch to Python. I typically teach like an intro to Python in 6 lectures, which is, fast track, but it is possible. And I've seen people that went from knowing nothing about programming to being expert in Python and machine learning within the course of 6 months. So I had a student who was had a bachelor's in film studies and now works in data science and machine learning. So it's a possible switch, and Python is just one step along the way, and it's probably a relatively easy step for you to make. And the nice thing is a lot of the things we will see today and tomorrow are kind of like prepackaged. There are wonderful tools available in Python that make it very fast, very easy to work with text that are highly engineered and developed by teams that really try to make this a performant tool and library.
Awesome, thank you. And there are like a couple reminders about could you please share the links on the papers that you mentioned? Yeah. And Marcos, asking about a book or like a draft version for teaching. I don't know, probably you mentioned something about that. And
yes, I shared that in the, I think it was shared in the emails, but I'll put links here in the, somebody posted the link to the first book. There's a second book coming out later, but I'll also share a link to the lecture notes of my regular classes that capture some of the same material.
Awesome. And we will copy and paste this information to the YouTube as well. So you guys don't worry, you'll get this info as well. And there is another question from YouTube, but maybe it should be addressed later when we move to like coding. But the question is about Python libraries and the fact that there are so many Python NLP libraries, and maybe you can talk a little bit about the respective ups and downs of the various frameworks. For example, NLTK, Spacey, Genzim, but I guess you maybe we'll talk about it later when we will switch to Colab. I don't know.
Yeah, so we'll see that in Colab. Just really briefly, NLTK was the first that was developed. It really means the natural language learning toolkit. So it was designed to be a pedagogical tool that allows you to look into the code, understand what's going on, and sort of learn about the algorithms while you do it. It wasn't designed to be super performant. So it is oftentimes much slower. It has a nice support for a lot of different languages, and I still use a bunch of those things like stemmers and lemmatizers from NLTK. The standard, I would say, today for performant NLP is the Spacey library, which also has like increasing support for more and more languages, has a lot of wonderful tools, sort of analysis tools like part of speech, noun, verb, adjective, dependency parsers, what is the syntactic structure, named entity recognition, but also very good tokenizers and other things. And it's designed to be fast and efficient. And is constantly updated. And then there's Genzim, which is kind of more specialized. It has implementations of Word2Vec and Doc2Vec that we've discussed today. And it also has implementations for various topic models, which we will see tomorrow. So those are maybe the broad, differences between them. And I know there are also like other libraries that, I haven't even gone into yet, but like those would be the big three, so to speak, or the most well-known.
Great. Yeah, we don't have any more questions for now. Yeah, thanks.
All right. Then let's reconvene in 15 minutes. Bye-bye. back, everybody. Hope everybody is refueled and relaxed, at least a little bit. Before the break, over the break, I've posted links to the papers I discussed briefly. Those are nice starting points. Obviously, there's a lot more. I also posted a link to this is by now a slightly older iteration of the NLP class that I'm teaching. It has all the notebooks. Some of them, have changed by now, but they should still be workable. Occasionally, maybe the interface might have to be updated a little bit, but there's also a link to the lecture notes if you want to read into some of the details there. Okay. I see. Okay. Yeah. So, I mean, there's, different approaches to meaning, not just from linguistics, but yeah, also from psychology and sociology. They all, differ in, sort of the theoretical underpinnings and the conceptualizations. In the case of these algorithms that I've shown, I think it might be stretching it a little bit, searching for strong theoretical underpinnings in one line or the other. They do implement a form of sort of contextual similarity, but for example, in sociolinguistics there are I think 2, 3 or more different ways to contextualize meaning. So a lot of the times these algorithms are sort of a compromise between a theoretical ideal and a hypothesis and underlying theory, and then the engineering reality to make it work with the tools we have disposable at hand right now and the computational power, which might actually be a good segue into our second part of the class. So let me share my screen again. There we go. All right, so let's get started with the classification part of the classification. So we have taken our text, we have stripped it of all unnecessary filling material, we've sort of pared it down to the really essential words, and then we have represented this in a big data matrix where each row corresponds to a document and each column is one dimension, which either has or has not a particular meaning. And now we want to use this for classification. So let's zoom out. What do we do in classification in general? Well, we have documents, and then for each of these documents, we have a label that is attached to that document. We have transformed each of our documents into a row vector in some way, shape, or form. And so all of them together are data matrix X. So we have N, N is the number of texts we have, and the input, and D is the dimensionality of our data. And then we have a output vector Y, typically it's called Y, which has a numerical equivalent of each label. And this is a column vector. It has one row for each of the documents, but only one column. So these dimensions make a difference, because when we do linear algebra matrix multiplications, then the inner dimensions have to be the same when we multiply things. What we're trying to do here is essentially, we're trying to find a function, something we do to X, such that the result is this vector Y. So somehow we have to squish together the matrix X from the left and right, such that we end up with a one-dimensional column vector of the labels. And typically, what we do is we take X and we multiply it with a vector of coefficients or weights. Different fields call it different things. And that basically then results in Y. And so the machine learning part of this whole thing is to find W, the weight vector, the vector of coefficients. That is the learning part. X is given, Y is given, and then we have it. And so this vector, if we want to get from an n by d dimensional matrix to a n by 1 dimensional output, needs to have d by 1 dimensionality. So essentially, we need to have one element for each dimension in our input matrix. So this is essentially the weight we attach to each dimension, to each column in our input matrix X. And if we multiply essentially the values in each column of X with the corresponding value in W, and then we sum all of that up, we typically get a value that gives us the output label. Normally, we apply a thresholding function. We say, is it greater or less than 0 or 1? We can choose that threshold freely, but that then essentially translates it into, for example, a binary classification, yes or no, red or green. I don't know, on or off. We can have more than 2 output labels. Essentially, what we then do is we have one weight vector for each output class. So let's say we have 3 classes. We have positive, negative, and neutral. We have a weight vector for positive, we have a weight vector for negative, and we have a weight vector for neutral. And so our output then would be 3 numbers. One is the probability that it's positive, one is the probability that it's negative, one is the probability that it's neutral, and we would simply then choose the label that corresponds to the highest probability. But yeah, underneath it all, very, very simple, straightforward, lesson 1, linear algebra, multiplying matrices and vectors together. The only tricky part really is how we get this W. This is the fitting part. If you're familiar with logistic regression from social science, it's exactly the same process we're using here. There's one slight change. I've omitted the bias term or error term here, which typically gets added on at the end, XWT plus B or E. And that is slightly different in machine learning than from what it is in most social science formulations, but still very, very similar setup. We're going to talk about logistic regression here. This same setup holds, however, also for naive Bayes classifiers. It holds for SVM, support vector machine classifiers. It holds for neural networks. It holds for everything. It's really always the same idea. What do I have to do to my input in order to arrive at the output? And this thing, this function, which in this case is really only a weight vector, but it could be more complex. That function, that is my classifier, right? The nice thing is, once I have found this function, once I've defined this function, once I have defined all the values in my weight vector, I can apply this to new input data. So in prediction, we take a new input Z or C, depending on which side of the Atlantic you're from, and we apply our function that we found. Here, it's just a weight vector that we multiply with this new input, and we get our predictions. In machine learning, when we talk about predictions, we put a hat over it. So Y hat are our predictions. So let's say we have a new set of 2 documents. They have to have the same dimensionality as our original training data. We multiply that with our weight vector. Maybe we do some thresholding, and then we arrive at our predicted output, right? And this is essentially it. This applies to any form of classifier that what goes on in this function might be slightly different from classifier to classifier, but the underlying idea remains largely the same. So there are some questions.
Yeah, there was a question about what T means, but I think I handled it. Transpose, right?
Yes, exactly, transposed. Because the inner, if we multiply the matrices and the vectors together, the inner dimension, so the rows of the second element have to be the same as the columns of the first element. And so basically what we have to do is we have to take this vector, which should be horizontal, and we have to transpose it, basically make it vertical, such that this holds, because we multiply a K by D matrix with a D by 1 vector, and then the D basically cancels out, and we have a K by 1 output vector, 1 by K output vector. Or actually, it should be a K by 1 output vector. Yeah, sorry, this actually flipped here. Yeah. So T is transposed. Other questions?
No more questions.
Mm-hmm. Okay. So that was the hard part. Well, okay. So this is the technical part, right? In practice, you will see sklearn, which is a Python library, gives you a whole range of different classifiers that you can use, but they have it set up in such a way that it's basically always the same interface that you use. So you say classifier.fit, and then you give it the training data and the labels. And then you can say classifier.predict, and you give it a new input Z, and it gives you back the prediction. So, and it doesn't matter what kind of classifier it is, it's always the same setup. So that's kind of neat. That sort of, shields some of the complexity that is underneath. However, it's good for you to know what goes into it. You don't have to implement it. Like very few computer scientists implement these things from scratch every time because there's existing libraries, but you should understand what goes into it. So if you don't get the output you want, you should know what are the knobs to turn and the buttons to push and the dials to fiddle with in order to get the correct output. So the big difference, I said before, to social science applications of, for example, logistic regression, where we're interested in that weight vector, in the coefficient vector, which we can then analyze for statistical significance and for the magnitude to tell us, is there an effect of this particular independent variable on the outcome? And we want to arrive at a causal explanation. In NLP and in machine learning, we're only, quote unquote, interested in how good a classifier predicts the correct labels on an unseen new input data set. So if somebody comes and says, I have a classifier that's 70% accurate, this is good or not, right? Well, it depends, right? Here is the, X is the input, Y is the correct answer, and Y hat is the prediction. This is a classifier that is 70% accurate, right? Yes, it correctly identifies frog, deer, wolf, dog, bear, and fish as being animals, for example, but it fails on bird and cat. It also, falsely claims that stone is an animal, but it gets tree correct. So this classifier is 70% correct. This classifier is also 70% correct. Basically, this classifier says everything above that line is a positive example, everything below that line is a negative example. This is clearly a useless classifier because it just says for everything it's a positive example, right? So 70% accurate might not mean much. Could work very well, but could also be garbage, as we see here. So what do we use to assess how good our classifiers are? And so here we go into the basic statistics of true positives, false negatives, and true negatives, right? As a reminder, I have the matrix up in the top left corner. True positive means classifier says this is an animal, and it is an animal. We're going to use an animal classifier here. True false positive means it's not an animal, but the classifier says it's an animal. So it was false in saying it's a example of a positive class. False negative means classifier says this is an animal. This is not an animal, but in fact it is one. So it was wrong in being negative about it. And a true negative means this is an inanimate object, and the classifier correctly predicts it to be an inanimate object. Now, with this setup, we can compute a variety of different metrics that tell us how good our classifier is. And these are different metrics, and they tell us slightly different things. But none of them are wrong to use. It just depends on what it is you're looking at. So here are our true positives. These are false negatives. This is a false positive, and this is a true negative. Right? So accuracy simply takes all the true positives plus all the true negatives and divides it by the number of positive and negatives, or simply by the number of examples, right? So this is like how many animals out of all the instances have we found? There's another measure that says if our classifier says this is an animal, how many times was it correct to say that? That's precision. We can also say, we know there are 8 animals in this data set. How many of those did my classifier correctly identify? How many did it miss? That is recall. And then there is a joint measure of precision and recall, which is basically precision times recall divided by precision plus recall times 2. This might seem a little bit weird. Essentially, it's the harmonic mean between precision and recall. And so, it's oftentimes easier to have a single number to compare to. And so in that case, we would use F1, which is the harmonic mean between precision, how precise is my classifier, and recall, how general, how good is it, how sensitive is it. So let's look at some implementations on this data set here, on these predictions. Accuracy, here we get 7 correct answers, right? We have 6 true positives and 1 true negative. So that's 7 out of 10 examples. So accuracy here is 70%, as we've said before. Typically, it's expressed as a number between 0 and 1. If you want a percentage, just multiply that by 100. Precision here is 6 out of 7, right? We have 6 true positives. And we have 1 false positive. So we divide the true positives, 6, by the number of positives. So true and false positives, so that's 7. So our precision here is 0.86, right? So in 86% of the time, when the classifier said this is an animal, it was correct. Recall here is 6 out of 8, right? Again, true positives is 6. Here we have true positives and false negatives. So false negatives means classifier should have said this is an animal, but didn't. So there's 2 of those. So out of the 8 possible animals, our classifier correctly identified 6, or 75%. And the F1, the harmonic mean between precision and recall, is 81, 0.81. Okay, so these are 4 measures that we can use. Accuracy can be a bit problematic because if we have a very imbalanced data set, we can get a really high accuracy even though the classifier hasn't learned anything, it just always says this is part of the majority class. Precision and recall are a bit more precise. F1 is kind of like a joint number. Now, the important thing to note is that precision, recall, and F1 are target specific, right? So here, our target class was animal. We wanted to know how often does it correctly predict animal. If we wanted to predict inanimate object or thing, the setup changes, right? Because here, what is a true positive or a true negative, false positive, false negative, and so on and so forth flips, right? So we went from this to this. So let's redo the calculations. Accuracy stays the same, is not affected by the target class. However, precision, recall, and F1 change. Here, precision is 0.3, recall 0.5, and F1 0.4. So our classifier is pretty good on predicting animals. It's pretty bad at predicting inanimate objects. There was a question?
Yes. Can we use cross entropy for text classification as well?
Yes, cross entropy is used as an objective function, as an error computation in neural networks. And yeah, you could use that. Again, these are oftentimes things that arise by community use and by tradition. There is no, particular reason why you shouldn't use cross entropy. Oftentimes, people have just gotten used to reading precision, recall, and F1. But cross entropy is used internally in neural networks to compute how far off the mark are you. That's used in neural networks where you use cross entropy. Yeah. So absolutely possible. Just not usual to be reported.
Thank you. Yep, no more questions.
Okay, there we go. So because precision, recall, and F1 are target specific or class specific, right? We can average them together. So we can get an average precision, an average recall, and an average F1 over the two classes we have. Accuracy always stays the same, but precision, recall, and F1 can be averaged together. Now, there's two ways in which we can average. One is micro-averaging, where essentially we first compute the true positives, false positives, true negatives, false negatives for the animal class and for the thing class. We add up all those numbers and divide all those numbers. Accuracy here stays the same. It's kind of a pointless exercise just to show it here. For precision here, right, for the animal class, we had 6 true positives. For the thing class, we had 1 true positive. And then we divide that by the sum of 7 possible correct answers versus 3 possible correct answers. So that's 7 divided by 10. So that's 0.7. So the micro average of precision is 0.7. For recall, similar thing, actually also ends up with 0.7. And F1, well, also ends up with 0.7. In this case, that's very easy. This basically takes into account how large the class is. So we did pretty well on animals, and there are 7 animals and only 2 things. We didn't do as well on things. And the overall, the micro-averaged precision, micro-averaged recall, and micro-averaged F1 are dominated by the fact that we did very well on the larger class. And sometimes that is what we're interested in, right? Maybe we have a data set where one class is much larger than the other. And it's really important to us that we get a classifier that does well on that larger class. If it doesn't do as well on the smaller class, that's okay. We're willing to take that risk, right? But sometimes we say, we don't care how large the class is. Yes, one of the classes is much larger than the other. We don't care. We need to be equally good on both, right? That is macro averaging. What we do here is we first compute the precision, so again, accuracy stays exactly the same. We first compute the precision for animal, 0.86. Then we compute the precision for thing, add that together and divide by 2. So this is 0.6, right? So here, the fact that thing is a much smaller class than animal doesn't enter into it because we've sort of averaged those numbers together into a precision score, and then we average those two average precision scores. Same for recall, and the same for F1 here, right? So depending on what it is we want to use, so as a recap, accuracy always stays the same, doesn't matter, but is heavily affected by imbalanced data if one class is much larger than the other. Precision and recall are much more sensitive to differences, but have to compute it for each class separately. And then if we want a single number, we can average them together either by taking the class size into account, which is microaveraging, or by using attaching the same weight, the same importance to all classes equally, which is macroaveraging. There's no right or wrong here. It really depends on what our application, what our target of this thing is.
Dirk, are you switched off your camera, I think, accidentally?
Not deliberately.
Yeah, so we can't see you. I mean, we can see your screen, but we can't see you. Your camera is off.
Okay, wait.
Oh, now you're back.
Can you see me now? Okay.
Yes, yes.
I don't know what happened. Weird. I thought I'd switched it on earlier. Okay.
Yeah, you've been on. It's just at some point something happened. And we have one more question in the chat. Since I already interrupted you, does this work for more than 2 classes as well?
Absolutely, yeah, works completely for more classes. The basic takeaway is the same. Accuracy is not affected by the number of classes. It will be sensitive to imbalance. So if you have one very large class, that will dominate accuracy, but sometimes that is what you need. Precision, recall, and F1 have to be computed for each class separately and then averaged together either by micro or by macro averaging, but that is independent of how many classes you have. So you can have 2 classes, you can have 50 classes, doesn't matter, works either way.
Thanks, there's no more questions.
Mm-hmm. Okay, so let's go back here. All right. So one reason why I kept going on about, this like imbalance of classes is that a very simple baseline and something that is good to always compute to make sure your classifier is actually performant is to just say, okay, what is the most frequent class here, right? The most frequent class here is animal. So what would happen if I just write a quote unquote classifier that just whatever I put in always says animal? It doesn't even look at the data, it just says this is an animal, this is an animal. So let's see, right? So we can simulate this. This is called a dummy classifier or most frequent class classifier. So here we have a bunch of true positives and then 2 false positives. And we can go through our computations again. Our accuracy is actually 0.8, great. Our precision here is also 0.8. Our recall is perfect because we found all of the animals that are in there, right? 8 out of 8. And our F1 is 0.9. So what does that tell us? This data set is extremely imbalanced, right? And so if we use a very, very dumb classifier that just says animal for everything, we get really high scores for accuracy, precision, recall, and F1. So all of the classifiers we've shown before are actually worse than this dumb classifier, right? So this means, you know, in order to learn something more than just the basic prevalence of a particular class, you would have to find a classifier that gets an F1 that is better than 0.9, right? Because with a super dumb majority class classifier, you already get a performance of 0.9. And so this is like a good sanity check. Before you do anything else, this is sort of your null hypothesis, right? You basically say, assuming there is no learning effect, assuming there is, you know, nothing to be learned here, how good would I be, right? And that is sort of the number to beat then, right? So here our number to beat is, for example, an F1 of 0.9. So wrapping up, metrics, accuracy can be a bit too general, so be careful when you use it. When you see it and people don't report precision and recall, ask them. They might want to hide something. Not intentionally, but you know, sometimes they could. Precision and recall have to be computed for each measure, and then they have to be averaged either by micro or macro, and they tell you a little bit in more granular detail how good your classifier is. So how confident can you be in its predictions? That's precision. And you know, how many of the things does it find in the data? That's recall. One thing we have to be aware of with these classifiers is that they can overgeneralize, right? So they can produce too many false positives. For example, if I got a letter like this, you know, I could say, haha, funny, they got my gender and age prediction wrong. Okay, you know, false positive, that happens. The issue with this is that, you know, you could build classifiers for a variety of things, predicting, for example, political orientation, religious beliefs, or sexual orientation. And then, you know, these things would be, you know, a lot less funny if you get false positives. So, you know, with great power comes great responsibility. And, you know, doing a proper assessment of your classifier in terms of like how performant it is actually very important. Now people are also starting to use fairness metrics. So if we have different classes, different demographic groups present in our data, so we have examples that come from, let's say, Northern Italians and others that come from Southern Italians, can we compute what is the precision recall in F1 only on examples from the North and only on examples from the South? And ideally, those should be the same. Otherwise, our classifier might be, you know, demographically biased. Not because our classifiers are racist or anything, but because, you know, we haven't set them up correctly. And these tools can be used, these metrics can be used as diagnostic tools to make sure we have a performant, but also a fair classifier. So how do we do this? This is the important part, cross-validation. And there's a wonderful paper by Bocconi and Westphal. Yeah, I think it's Bocconi and Westphal. Why psychology should become predictive science. But you know, this applies to social sciences more general, where they basically argue that some of these metrics, some of these evaluation measures that are used in machine learning can actually be also useful as, for example, robustness checks in social sciences. And they have a couple of great examples and explanations. So I'll post the link later. Those are, you know, like great pointers. And this goes also to this larger discussion of like to predict or to explain, or a little bit of both. The idea in cross-validation is that we have our data set, right? We have the X, the data matrix with our examples as a big matrix, which, you know, each row is an instance. And then we have our labels, Y, which is a vector. And what we do is we split our data into a training and a held out test set. So we say, here's our test set. We're going to put this aside. We're not going to look at it. And then we're only going to train on the rest, right? And the splits are up to you, but typically it's like 80-20 or 90-10. Oftentimes what people do is they add like another set. So they say a development set where they say, I will choose all of the decisions that I have What is my pre-processing? Should I remove numbers? Should I reduce them to 0? Should I use embeddings? Should I use discrete representations? Should I use logistic regression or SVM? I'm going to try out all of those different combinations by training on my training set, and then I'm going to have a development set, and I'm going to check on that. And then once I am satisfied, once I get the best performance on this development set, then I will go and report what performance I get on my held out test set that I took away all the way at the beginning, right? That sort of is like a good way of protecting yourself from overfitting, from focusing too much on one particular random regularity in the data, like a spurious regularity in the data. Problem with this is, of course, if you have 10,000 examples, fine, no problem, right? You put 2,000 aside for training, 2,000 for dev, and then the remaining 6,000 you use to train your classifier. Easy peasy. But especially in social sciences, especially if we have data that was difficult to collect, we have much smaller data sets, right? So what do you do if you only have like 1,500 data sets? I don't want to put aside a lot for training and dev, then I have nothing for dev and test, then I have nothing left for training. This is where k-fold cross-validation comes in. Essentially what we do is we take our data and we split it into k equally sized folds. So here k is 3, so we split our data into 3 parts. And then we train 3 different classifiers. The first classifier we train on the blue and the green part and evaluate on the pink part, and we save that number. Then we create another model that we fit on the blue and the pink part and evaluate on the green. And then, fold 1 and fold 3 and evaluate on fold 2. And then we have another classifier that we train on fold 3, the pink one, and fold 2, the green one, and evaluate on fold 1, the blue one, right? For each of them, we compute, for example, the F1 score. Maybe we get a good score on the first set, less good one on the second, and a decent one on the third. And then we simply average over those 3 models and report the average score that we got. Essentially, what this does is it makes each instance in our data a test instance once, right? If you look at it, each fold has once been the test fold. And it basically says, how good would we be on average if we had different configurations of our data? How well does this generalize? This is a much more robust estimate than using a single dedicated test set that we set aside at the beginning. Does this make sense? Okay. So let's talk about baselines. I've talked about the most frequent sense baseline to compute sort of the dummy classifier. Here it is again, right? So this is the number to beat. There's another baseline, which I sometimes call the Hulk. It's dumb but powerful. You take very, very simple input representations. You just look at character combinations, 2 to 6 characters. You weigh them with TF-IDF. And then you run a simple logistic regression with L2 regularization and balanced class weights. We're going to get into that in a second. And then you check what is the performance of this. This is a super simple, this is like 5 lines of Python. But interestingly, this thing is sometimes really, really hard to beat. So I have seen several examples now where the performance of this classifier was the same as like a tricked out neural network with several layers and like the latest technology. And then in the end, the neural network beat this dumb 5-line classifier by, a few percentage points after, lots of engineering and, lots of training. So using this dumb classifier can give you, a good, oftentimes can give you, pretty good performance. And it's sort of a useful stress test to see, how much am I actually learning with a much more fancy, complicated model. There was a question?
Yes, Johannes asked questions on how do you interpret the results since you have created different models for the K-fold methods.
Yeah, so you could either interpret the results on the, well, I mean, if you want to interpret the results, you could also average the coefficients of the different models, right? If you want to do an interpretation. And then you just take the average coefficient over those three models and use that in your analysis of statistical significance, or, you know, like the impact or the causal explanation. So that would be one way.
Thank you. There's no more questions.
Okay. All right. One thing we have to talk about is regularization. Regularization is this part that I emitted earlier, right? So we said, okay, our output labels, our y, our vector of labels, is the result of some function that we apply to the input x. And typically this function is take the input, multiply it with a weight vector or coefficient vector. And then oftentimes there's this plus e or plus b, different disciplines call it differently. It's either called the error term or the bias term, or, you know, there are other terms as well that are used for it. And this is oftentimes kind of like a fudge factor, right? Where we say, okay, so in order to get this output, we take the input, we multiply it with you know, like a defined set of weights, but there's also this little noise thing that's going on. Oftentimes in social sciences, we use E to be Gaussian randomly distributed noise around, so jitter around each of the data points. That is one way of thinking about it, but that is an assumption that assumes that there's normally distributed noise. In machine learning, there are other ways of defining this bias term. And rather than saying it is random to some extent, you say it depends on my weight vector. So basically, you're giving your model a harder task. You're saying, hey, model, I want you to find a weight vector that explains the data I've shown you, so that creates a link between the input and the output. But you also need to satisfy an additional constraint. Namely, I want my weight vector to adhere to certain constraints. And so what are those constraints? Well, an easy one is to look at sort of the norm of the vector. Remember, the norm of a vector is basically its length in space, right? We can plot this vector as a point in a d-dimensional space, right? And so the norm of this vector is basically its length. What I can do is I can say, I am interested in a vector that is very short. I want a very short vector. That's the L1 norm of the vector. And the best way to get that for the model would be to find a weight vector that has a lot of zero coefficients, right? So coefficients that just don't affect the output at all, right? This is called a sparse vector. The way the L1 norm is defined is we simply take this vector and we just sum up all of the numbers in that vector. The more of them are zero, the smaller that number is going to be. Very easy. This is often used to do variable selection, right? To throw out features that don't actually matter, right? So if you use the L1 norm to define your constraint on the weight vector, your error term, then you will end up with a coefficient vector that has a lot of zeros in there. And then you can ignore those features. Basically, you can say these are features that are not interesting. Instead, you could use the L2 norm. The L2 norm basically takes each element in the vector, squares it. So you remove any negative elements, you make them positive. Negative x squared is positive. Then you sum everything up, and then you take the square root. What this does, the best solution to for finding a weight vector under this constraint is a weight vector that has some weight on each dimension. Not like a lot of weight on one and then nothing on the other, but a little bit on everything. Not too much, not too little, just right. So in practice, this L2 regularized weight vector, often it's also called ridge regression, whereas the L1 is called lasso regression, tends to perform really, really well in classification tasks. And in fact, in sklearn, in Python, the standard implementation of logistic regression is ridge regression, which uses an L2 regularization. Typically, there's a value attached to the strength of the regularization, so we can, sort of enforce this constraint more or less. A nice way to think about the two different regularizations, and there are others that I don't want to get into now, is there's lots of different ways in which you can have a good L1 regularization. So there are lots of optimal L1 regularized weight vectors. So those are the red or the blue or the yellow. They all have the same length. If you're in a grid, there are all these different ways of getting from A to B, and they all have the same length. But there's only one optimal solution, which is the L2 regularization, which is the green direct line, which basically just goes straight from A to B as the crow flies. We can also use these things for feature selection. So we've talked about discrete representations, right? Each column in our matrix can be a particular term. And maybe not all of them are useful, right? Maybe we want to throw some of them out. We can use L1 regularization to find out which of them are not useful, but there are also other things. We can use chi-squared. So we take each feature, each column, and we measure the correlation of that particular feature with the output. This is often also called wall statistics. Chi-squared is essentially the correlation between two random variables. And then we can, we get a value for each of the dimensions, and we can just take the top k dimensions, which have the highest values, right? So that way we can reduce our input space. Because having fewer variables means it's easier to explain, but also probably performance is better and more robust. So here, for example, if we just wanted to take the top 5, we could reduce our input to this 5-dimensional vector. We could use a dimensionality reduction technique, something like singular value decomposition or principal component analysis, non-negative matrix factorization, or multidimensional scaling. I don't want to go into these in detail now, but essentially it says, okay, what we see, can be explained by fewer dimensions than we see here, and there are analytical methods to find those fewer dimensions. And so, we could use that and just find the 5 most informative dimensions and then reduce it. There was a question?
I don't think so. I think we handled this last one about k-fold method again.
Oh, okay. And then last but not least, there is an algorithm called randomized logistic regression. Basically, you take an L1 regularized logistic regression, you run it on different subsets of the data, and you just check, which of my dimensions get 0 coefficient, and then you basically count out of my whatever 500 or 1000 runs, which dimension, how often of the time did a dimension get selected as a non-zero coefficient, right? So here, first dimension got selected in all 3 of our runs, Second dimension only got selected in one run, so 30% of the time. And then you can basically use this average to say which of the dimensions is a stable, general, and informative dimension. We actually implemented this. There's a website, wordify.unibocconi.it, where if you have textual data, you can use this algorithm under the hood. You just upload an Excel file with your text and the labels, and it will then tell you for each label which are the most informative terms. So it does this variable selection. Okay. So this was quite a lot, but essentially, in order to do classification, we first want to pre-process the data, remove noise and unwanted variation while keeping the informative bits. We can represent our data as sparse, discrete vectors that are interpretable, or as dense continuous vectors, which are oftentimes they're more compact, they're usually smaller, and they're performative, oftentimes better. Sorry, but they are harder to interpret. We need to look at different metrics to find a good classifier. We need to compare to baseline, sort of our null hypotheses, to make sure we're not, reporting a result that actually, could be easily beaten by a very, very dumb baseline algorithm. We need to regularize our models so they generalize better to unseen data, so they don't overfit to the particular data configuration we have used in our example. And then we can do things like feature selection and dimensionality reduction to improve performance further if we're not happy. For a lot of the things we've discussed, this is sort of the book that has already come out. This is the first part, Discovery and Exploration. So this covers things like word embeddings, document embeddings, TF-IDF representations, also things like dimensionality reduction, topic modeling, and other things. So this is already out. If your institution is subscribed to Cambridge University Press, there are links to that. The second part should come out later this year, and that's going to focus on classification and prediction. But in the meantime, you can also use the class materials and the lecture notes, which cover a lot of the same material. But if you want to cite something, then this is your chance to cite something. All right, that brings us to the end of this part. Are there questions at this point before we switch to the notebook?
Nope, no questions so far.
All right. Does everybody have access to the notebook? The Colab notebook?
Yes, we send it to everyone, but we will also put it in the chat now. So we will.
Okay, great. Mm-hmm. All right, so let's switch to that then. Or should we take a 5-minute break before we go to the notebook?
Yes, it's up to you. So if you want to take a 5 minutes break, we can also do
let's take 5 minutes. Let's settle before we switch gears. Yes, need coffee. All right, excellent. Get a coffee, refuel. I'm going to get a coffee myself. And I'll see you back in 5 minutes with a notebook. appeals
We
to.
actually have a question.
Yeah.
Sorry. It came last minute before the break. So the question is, could you maybe talk a little about other ways of engineering features for NLP besides word count and TF-IDF scores?
Mm-hmm.
And specifically, the person wants to know about using both features such as the TF-IDF factors we used in the Colab with other, let's say, unconventional features like metadata of the original text in a classifier.
Mm-hmm. Excellent question. Yeah, absolutely. So neural networks and things like word embeddings and document embeddings have taken this feature engineering part a little bit away, and it's all like data driven. Before that, the quality of a model was oftentimes dependent on the quality of the features you managed to extract and define and think of. This is really where your creativity comes in, right? So in social sciences, typically we want very few features because we don't want confounds, and we want to sort of really, nail the explanatory causal story here. In machine learning, we're less constrained with that because we can use things like feature selection and reduction. But there are other things that you can use. So people have shown that using the form of a word can be very useful. So you just replace each character with an X. But if it's an uppercase X, you use if an uppercase character, you use an uppercase X. If it's a lowercase character, you use a lowercase x. If it's a repeated character, you just use one version of whatever it is. And that sort of gives you just the gestalt, the outline of a word. Using that as feature can oftentimes be useful because it ties together certain patterns. You can use you can analyze the syntactic structure of a sentence, right? What is the subject? What is the verb? What is the object? And then you can use jumps in this. It's a graph over the sentence. You can say, give me just the combination of the subject and the verb, and I'm just going to make a feature out of that. Or give me just the verb and the object, or the subject and the object. Or give me like any jump in the tree as a feature, which sort of introduces a bit of structure and syntax into the representation. So these are ways you can get creative. So I was going on about this all being linear algebra. If we've done all of these things, we created our data matrix X, right? But we also have a separate matrix of meta information, right? So for each document, we have the date it was produced, the gender of the author, the intended outcome, I don't know, I'm just making things up, right? Which is a separate matrix, right? What we can do is just glue those two matrices together. They have to have the same number of rows, and just make a bigger matrix out of it, right? Absolutely possible. I've done that before, sometimes to good effect, sometimes less so. But yeah, absolutely possible. So your creativity really, and your knowledge of the domain, your knowledge of the problem space really comes into what you can come up with as features and what you know will be interesting and useful features. Sometimes this can be surprising. NLP, which is mainly concerned with language, initially thought that having good knowledge of linguistics would just solve everything. There's this infamous and disputed quote, though, that one of the engineers at IBM said, every time I fire a linguist, my score goes up. So that linguistic knowledge actually wasn't helpful. Now there's a little bit of a pendulum swing in the other direction, where people say like, well, we have all of these great learning algorithms, but we oftentimes waste cycles and waste energy of the algorithms to learn things we actually don't need. And if we had some knowledge of language, like an inductive bias, some prior knowledge about the problem space, we could sort of tailor the algorithms better to learn the important bits here. So, it always goes a little bit back and forth, but at the end of the day, knowing more about your problem space actually does help quite a bit in general. I studied linguistics originally. I have a master's degree in linguistics before I switched to computer science, and I often found it helpful in, addressing a problem. But you need a little bit of both. You need the engineering side, you need the linguistic side. And in computational social science, you need the computational side, but you need the social science, just as much. So your creativity knows no bounds in terms of like feature engineering.
Yep, no more questions.
Mm-hmm. Oh, sorry, there was another aspect, right? The TF-IDF. I should say that there are different ways of formulating TF-IDF. It's in the book and in the lecture notes if you want to check that out. There's also other ways, right? So you could use the raw counts. That typically is not super helpful. You could normalize by, the number of words in a sentence. So that longer sentence, you could use the raw counts, but normalize by the number of words in that instance. So, that way you get like a relative count that can be more helpful. You can have something very crude, just a binary indicator. Is this word in there? Yes or no? And I don't care if it's more than once. I'm just going to say yes or no. So there are different ways of defining the features. Typically, though, it really oftentimes depends on what exactly your problem is. But on average, TF-IDF tends to work best. Another thing I should say, instead of using words as units for your TF-IDF counts, as I've mentioned in the Hulk, you can use character n-grams. So you just slide this character window over it, like 2 characters, 3, 4, 5, 6, including white spaces, everything. You don't have to pre-process much. Just slide that over, which is a bit unintuitive, but what it does is it does capture a lot of morphology. So inflection, so little snippets at the beginning and end of words. So in the beginning, you might have things like miss or anti or con or something like that. It will capture those. It will also capture the inflection patterns, so ing or s at the end or ed at the end in English, right? And it works surprisingly well. It is theoretically a little bit unsatisfying because it's just like character snippets. But if you think a little bit about it, they do capture phonological, morphological, and other aspects of language. So that can actually also be useful. Other questions?
Nope, no more questions.
All right, excellent. Then I would suggest let's take a look at the notebook. There we go. This started kind of as an inside joke, but I like to start some of my lectures with like misattributed quotes. This is really only funny if you know who Noam Chomsky is and who the original quote came from, but I'll leave that to you as an exercise to the reader. Let me actually increase the size here.
Dirk, sorry, there just another question popped up.
Yeah.
What about engineering a model for morphology-rich languages, such as Russian? Is it usually a good choice to add the grammatical tags to the words in modal?
Say that again, add the grammatical.
Sorry, is it usually a good choice to add the grammatical tags to the words in the modal?
Oh, like underscore noun, underscore verb, or like the aspect or something like that. It can be, yeah. I have done that before, and it can be very useful. As an example, the English word round can be a noun, a round of applause. It can be an adjective. This table is round. It can be an adverb. I got there round 5 o'clock. And so distinguishing that by adding underscore adjective, underscore adverb, underscore noun, or can be a verb, I round up to 5. That can actually help introduce some information and can be very useful. Yeah. So is absolutely a possibility. Yeah. Very, very good idea, and oftentimes also done. Yeah.
Yeah, thanks. No more questions so far.
I wanted to increase the font size here. Oh, is this here? Settings, editor. Let's go big or go home. Does this change anything significantly? Okay. Okay, so this is the notebook. Here's a rough overview of what we want to do, right? Pre-process the text, get a label, vectorize everything, learn this mapping from input to label output, and then evaluate the model and predict new data. Here's a little checklist, which you can go through. This sort of like, it's like a very bare bones overview of what you would do, to start out with your data. I say here 2,000 instances. You should have at least 2,000 instances. That might sound like a lot, but the thing is, if you have a single sentence, right, you have one instance and maybe each word is different, right? So your ratio of number of instances to size of your vocabulary is very bad, right? You have one instance and a lot of different words. As you add more instances, yes, you will add more words, but you will at some point reach the point where you've seen most of the relevant words, right? So adding more instances will not increase your vocabulary, but it will increase the information about that vocabulary, right? And again, this is typically like a logarithmic curve. So in the beginning, like every instance adds more features, but at some point it peters out and becomes very flat. And like at some point, if you add more instances, you're not going to add any more words, right? This is an indirect outcome of the zip curve that we discussed earlier. But 2,000 is typically the point where this stabilizes, right? Where you have enough information about each word in the vocabulary to make it count, but you don't get like weird outliers and you don't get too much information. You can run everything with fewer examples. The statistical validity, the robustness, the generalizability of this suffers a lot. So the more data you have, the better, right? Just as a general outline. So if you're faced with the question of like labeling data, coding data, annotating data, aim for 2,000 or more if possible. And yeah, that is quite a lot, but if that allows you to then analyze millions of data points, it's oftentimes worthwhile. So here we're using a data set of wine reviews from Kaggle. Oh, I forgot to put in the link here. I'm going to do that. Basically, it's from, I think, Wine Spectator, from a website where somebody scraped all of the descriptions of different wines, and they added which country the wine is from, what variety it is, so Chardonnay or Riesling or whatever. And then, like the sub-region, like the Rhone Valley or, whatever, Bergstraße, I don't know. And there's a bunch of other information in there. I've added another column to this data set where I basically pre-process the data, and normally we would do that ourselves. And I've uploaded this to my website. You have to, in order to use the notebook, you have to get that data. You have to integrate it here. If you just execute the cell, then it's loaded into the memory. This cell here is how I pre-processed the data. I defined a clean function where I basically just applied to every text. And essentially what it does is it throws out everything that is not a content word. So only words that are nouns, verbs, adjectives, adverbs, proper names, or this category X, which is sort of oftentimes foreign words, or sort of like expressions like oh or oops or something like that. Okay, so we've imported our data. We're using pandas, which is a library that allows you to deal with data. We just read it in, and here we print out the top 5 rows with this head command. So here you can see we get the different countries, US, Italy, and others. This is the original description, abbreviated. We have some designation, I actually don't know what that is. The points it got in the Wine Spectator magazine, the price, I guess this is dollars per bottle, I don't know. The province it comes from, the regions it comes from, then the variety it is, what the winery is that produces it. And then here, this is the cleaned description. And you can see if you compare the description to the clean description, how, is gets reduced to be, this is thrown out because it's a stop word. And we sort of, are left with this sort of rudimentary way. We're going to split our data into training, dev, and test. I'm going to use 50% of the data as training and then 25 each for development. So to come up with the right settings for the pre-processing and for the model selection. And then the test size is what we would report in the end. So this is basically just preparing the data. So we get 10,000 training instances, 5,000 development, and 5,000 test instances. You could also use these predefined functions from sklearn, stratified k-fold or stratified shuffle split, which basically creates subsets of the data which have the same proportions of all the labels in each fold. So that oftentimes, can make it cleaner and easier to work with. As you can see here, we have a bunch of different columns that we could predict. For now, what we're going to do in this notebook is predict the country that this wine comes from. So we're going to use this column and set that as our training column. So we say out of our data, this is the target. So here, this is a sample of the first 10 instances. Most of them are from the US, one is from Italy. And we're going to do the same for development and test. Let's look at the proportion in each. So we see around 20% in each training, development, and test is from France, around 20 from Italy, around 7 from Spain, and around around 50% is from the US. So this is a very imbalanced data set, right? Quick question already, you can sort of mull over in your head. If we use the most frequent label classifier, which label would we predict for everything, and how good do you expect it to be based on these proportions of the labels? First thing we do is we transform our input data, our pre-processed data, into TF-IDF scores. So we import this TF-IDF vectorizer, then we instantiate one. We say we want unigrams to bigrams, so all single words and all combinations of 2 words. We say we're not interested in any word that occurs fewer than 0.1% of the time. So this is the minimum document frequency a word needs to have, or a bigram or n-gram term needs to have in order to be included. And we're also not interested in words or terms that occur more than 70% of the time, or in more than 70% of the data of the instances. Why do we do this? Well, we don't want words that occur, I don't know, only once or twice in the data, because they don't generalize, right? The only thing they tell us is that, well, it's this document and nothing else. So that's why we have a lower bound, like a minimum frequency. We also don't want words that occur in more than 70% of the cases, because really, what do they tell us? If a word occurs everywhere, it basically says nothing. If you see that word, it doesn't tell you a priori what instance it's from, right? So you could even lower this number more if you wanted to. We want to set the analyzer to word rather than character. And we're going to set this sublinear term frequency to true. What does that do? Well, essentially, it uses the logarithm of the term frequency, because you will have some words like the and a and whatever, wine probably, that are super, super frequent, that are total outliers, and that will kind of ruin the numbers for everybody. So by taking the log of them, we're squashing everything into like a smaller range, and that way we get sort of nicer numbers. Once we have our vectorizer defined, we call this joint fit and transform function on our training data. And we call that X train. And then we can print the shape of it. We have 10,000 rows. So shape of a matrix gives us the rows and then the columns. We have 10,000 rows because we have 10,000 instances. And we end up with round about 5,000 features, which are the unigrams and bigrams that we've extracted that occur, at least in 0.1% of the data, but not in more than 70% of the data. And then, once we have this vectorizer set, we use only the transform function. So we fitted it on the training data, and then we apply the same transformation, the same vocabulary to the development and to the test set. And we get, the same shape for both. So we have 5,000 development and 5,000 test examples. Was there a question?
Yes, there's a question from Rinha. Is the decision to use log transformation domain dependent, or is it just a common technique in most cases?
I would say it's probably independent of the domain. It's a good question. So remember when I said that this zip distribution, that like some words are super frequent and that the next frequent words are much, much less frequent than those very frequent ones, and then it goes down from there. That is basically always the case. Doesn't matter what domain you use. So when you're working with language, and so the log of that basically undoes this weird shape and sort of makes it into a nice flat line or like a slope. And because basically every language data follows this zip distribution, using the log kind of counteracts that. So I don't think it really depends on the domain. You can try it without. Again, this is a researcher degree of freedom that you should, change and then observe the effect on your development set. Yeah. Okay. Did that answer the question?
Yes, it did. Thank you.
Okay, great. So we talked about the Hulk, right? Or the dummy classifier first. We import that from the helpfully named library dummy in sklearn. We say use the most frequent label. Again, like any classifier, it has a fit function. So here we initialize it, then we fit it on the training data, the training input and the training output. Our dumb predictions are, whatever the most frequent class is. So this is only going to be US because that's the most frequent class, right? And then we're going to call this classification report here, which we give the, so we run this on the development set. So we predict everything on the development set. And then we predict, we compare it to the correct answers of the development set. So this is the correct answer, a gold standard answer. And we compare that to our dumb predictions. And you can see this classification report gives us this very nice, can I make this bigger somehow? I apologize if this is not super visible. I try to set set up the font size, but that seems to be only for the code cells, not for the output. So here we get some output, and now you know how to read these things, right? You have precision, recall, and F1. Support means the number of instances. Here we basically say for everything, it's the US. So our recall for the US class is perfect, right? It's 1. The precision is 0.53, so the F1 score here is 69 for the US, harmonic mean between precision and recall. Accuracy, you can see here, is the same for anything, doesn't matter. Accuracy of around 53, which is the prevalence of the US class in the data. And then you can see the macro average is this. So we macro average over all of these classes weighting each class equally. So we get a performance of roughly 13%, which is 1/4 of this one, or the weighted average, which is the micro average, essentially, where we sort of take into account how large each of the classes is and how well we do on it. So this one is better, right? The precision here is higher because it's dominated by all of these US instances. Right? Okay, so again, a priori, neither macro or micro or weighted average is better. We just need to pick one that we want to focus on. My suggestion would be, we want to be equally good on all the country wines. So we're going to choose macro average as our target. Okay, so having a low number here with a dummy classifier is good because that means, okay, this is not a solved problem. There is some headroom where, we can do better if we apply a better classifier. Okay, so let's try that. Let's get a logistic regression classifier. Let's set it up. We're going to parallelize it. This n jobs means parallelize it on multiple cores. We're going to use the automatic setup for multi-classes, and we use this solver. You don't have to specify anything. You can just leave all of this blank. Then it's going to give you some warnings that you should define these things. Otherwise, it will use default values. You can ignore that. LBFGS is line blah Goldfarb something. It's a way to find the correct weight vector as output. And so with this time, it tells us how long it takes to fit this. So we have 10,000 examples. It took us, around 45 milliseconds to fit the data and then to display it 2 seconds. So that's pretty good. We also get information about the classifier. We don't weight the classes. Our tolerance is 0.0001. The regularization weight we use is 1. So we use L2 regularization and it's weighted by 1. And yeah, everything is basically default settings. There was a question?
The question was that there is an error when a person tries to run the classifier. So I'm just trying to ask what type of error, because it's going to be really hard to figure out how to help without knowing what error it is.
Yeah. So if you want to run the notebook, I think you have to download it. So you have to first go here and then save a copy and drive. Because you can't run it, otherwise we would be overriding each other. So you need to make a copy in your own Google Drive. Theoretically, otherwise it should work because it's run on the same server. So if it works for me, it should work for you, because if we're running it on Google Drive.
Okay, the problem solved. It wasn't downloaded. Yes.
Oh, okay. Yeah. You have to execute all of the other cells above. So you can here run all before the current cell. That typically makes sure that all the information is available. We can ask the classifier what are the classes you have detected and that you're using, and it's the 4 classes that we expect: France, Italy, Spain, and the US. Great, all good. We use our fitted classifier and we predict on the development set and let's output the top 10 predictions and then do the classification report on the correct answers compared to our predictions. Okay, so here are the outputs that we get. And this is the classification report. We said we were going to focus on macro average. Before that, our dummy classifier got 17% F1, macro average, and here we get 86. Whew, okay, pretty good, right? So this is nice. We can dive a little bit more into these numbers. Precision seems to be pretty good, around 90 for all of them. So when it thinks it's from France, Spain, Italy, US, it's usually right in around 90% of the cases. The recall varies a little bit, right? So we find most of the French wines, most of the Italian, and pretty much all of the US wines. We're not very good at detecting Spanish wines. So some of those get misclassified, right? So maybe there's some room for improvement here. Sometimes instead of getting the class output, we just want a distribution over the different classes. For that, we can use this probabilities on this data set. And then we just put it into a pandas data frame with the classes as columns, and we're just going to display the top 5 rows. So here you can see these are our classes, and these are the distributions. You can see here, first instance, 57% probability that it's the US, 32 that it's Italy, and then around 6% and 3% for France and Spain, respectively. So it decided, the maximum here is US. So the output also for the first instance was US. Class output for the second one was Italy. So we would expect the second one to have the highest probability for Italy. And yes, it does. 79% probability that the second instance is from Italy. Everything else, very unlikely. US, very, the most likely, but only around 10%.
We have a question.
Yeah.
How does the logistic regression classify multiple classes, given it uses sigmoid function to squish things between 0 and 1?
Yeah, excellent question. It trains essentially one classifier for each class versus all the rest. So under the hood, Python trains a France or not France classifier, an Italy or not Italy classifier, a Spain or not Spain classifier, and a US or not US classifier. And it basically has a separate set of coefficients for each of these classes. But for each class, it does the squishification, the sigmoid, to basically check, is this France or not? And then this output essentially, takes the logouts of those different classifiers and then normalizes that to be one probability distribution.
Thank you. And no more questions so far.
Okay. Sometimes you might want to...
Actually,
oh, yeah.
Sorry for interrupting, just popped up another question. Why not to use multinomial logistic regression instead?
You could also use that. Yeah, you can set that. So here we set the auto, but there is a attribute that you can set for multinomial. It's up to you. Yeah. Again, it might depend on what you want to show, explain, or predict, which one works better. There are options. So all of these functions here, if you hover over them, you can get a little tooltip that shows you information about this particular class. Right. So here you can read through all of like a description of what it is. We can open it in a new tab. So here you get the definition, you get a description, and then you get an explanation for all of the parameters. And this is a good practice to basically, read the docs and like understand what is possible. Let me see where, so we talked about the multinomial setup here, right? So you can set the multi-class to auto, one versus rest, which is what I just explained, or multinomial, right? Which is the other option. You just compute a multinomial distribution. The question is whether, like, what kind of output you want, but it also depends a little bit on the solver. So on the algorithm you use to find the correct coefficients or weights. Other questions?
Yes, if you would follow the k-fold cross-validation method, and how far would the coding differ, and what would it make sense in that case?
Yes, we'll see. Wait, do we have that? Yeah, so we actually use this down here when we do a grid search over all the parameters. This parameter here, CV, is cross-validation, which means take the data, do a 5-fold cross-validation, so make 5 parts of the data, and then train on 4 and evaluate on the 5th, and do that 5 times, average over it using F1, micro F1 as your criterion. And so this is in here. In general, I think it's a great idea to use cross-validation, like k-fold cross-validation, because it gives more generalizable results. If you have, so if you have a data set that's large enough, the larger a data set gets, theoretically, it should get more generalizable. It should get more representative. Bracketing corner cases where that's not true. So if you have a data set of our size, having 5,000 test instances probably is like a relatively good, representative sample. If you have smaller samples, then using k-fold cross-validation is a great idea. You should definitely do it because you're not dependent on a, sort of random, arbitrary composition of the training or test set, which might or might not be lucky or unlucky for your classifier. So using cross-validation can give you like a more robust, a more generalizable, a more informative measure of how performant the classifier is.
There is like additional comment on YouTube. The person thinks that it also depends on whether the classes are balanced or unbalanced.
No, that shouldn't make a difference for whether you use k-fold cross-validation or like a held out data set. It is true though, if you have like a very imbalanced data set and like your training data has a different split than your test data. So if it's 50-50 in training, but then 90-10 in the test, the distribution of classes, then yeah, that's very bad. So that's why you could use this stratified k-fold, which would make sure that you have the same distribution of classes in the training, dev, and test. And that way, your classifier is not being thrown off by like a weird sample.
Cool, no more questions so far. Thanks.
Okay. Speaking of class balance, this is one of the ways. So now, this is basically it. This is done. We're done, right? So we got 86% macro average. Okay, maybe this is enough for us. We're going to be like, let's go home, open a beer and celebrate, right? However, you might say, maybe I can do more. So there is a parameter that is often very useful. It's called class weight, and you can set that to balanced. What this does is it basically will upweigh rare classes. And if your classifier makes a mistake during training on very rare classes, it will weigh that more heavily, and it will downweigh errors that it makes on misclassifying very frequent classes. So in our class distribution, right, I think Spain was very rare. By making a balanced class weight, we're basically going to multiply any error we make on Spanish instances and make them weigh more heavily, and so influence the classifier to get those rare classes correct. And so if we add this and we just rerun the whole thing, we can basically see here that we're actually improving our macro average from 86 to 87 and our weighted average even to 90. And largely, you know, we'll see that this is due to us getting a better recall for Spanish data. Our precision suffered a little bit here, but on the whole, this shakes out to be better, right? So using balanced class weights is an easy way oftentimes if you have an imbalanced data set to get better performance. We can play around with the regularization strength. So we're using an L2 regularization, meaning I want a weight vector that uses all of the available information, but doesn't put all of its eggs in one basket and like overuses one particular feature. We can, you know, determine how strong that regularization is. Is it very strong or less strong? And we can sort of iterate over a number of strength, like constants that we multiply this error term with, and basically look at the outcome and see sort of how what the effect is. So with, you know, a weight regularization weight of 50, our micro average is 91. We get slightly better if we go down to 10. So here it gets slightly better. And I think that's the best score we get. Yeah. So you can experiment with that, right? So this is another parameter you can tune. Basically, how strict do I want my classifier to be in terms of like distributing its coefficients, its weights over all the input features or not. We can put everything together over all of these parameters. So we can search over a combination of the class weight, of the regularization parameter and the class weight. We can run all of that. It will run a 5-fold cross-validation using micro F1. We can also change this here on all the data and basically save the best available classifier in the end, the best combination of features. The thing to be mindful of is that we want to, you know, do this on just on the training data, and then we can evaluate that on the development data. And really the test data, we haven't touched the test data at this point. We only want to use that all the way at the end when we report our results. So this is still running. I see that officially we've reached the end of the class. There are a couple of more examples in here with some explanations in there. Maybe the most interesting one is probably going to be, let me see. Yeah, so here we did the grid search. We're getting, you know, slightly better performance. We can do feature selection. We can do dimensionality reduction, and we can do this inside. So basically what we can do is we can get a sense of which of our features are the most informative ones. So basically we're getting our features, we're selecting the coefficients that we have gotten from the best possible classifier, and then we're putting all of that together into a data frame, which we're going to display. So we see for each feature, which class does it best predict, and what is the prediction strength. So this can sort of inform us about, you know, what is the which words, which terms are the ones that best predict French wine, Spanish wine, US wine, whatever. So this can be a way to give us insights. Are there questions at this point? So otherwise, I would say we could stop it here. I'll leave the other parts for you to play around with. Obviously, if you have questions, can always send me email. I have posted a couple of examples, a couple of things that you can look into to deepen your understanding of what's going on. Really, we've only scratched the surface of what is going on. There's a lot more to be said about like ways to improve the performance, about the ethical ramifications of using these tools, about different applications to social science questions. But I hope that this gives you a little bit of a better understanding of what goes into it, and some threads to start pulling at and to unravel, and maybe a taste of what you can do. And with this notebook, you can play around with and try it on new data on your own thing. By the way, here, this is sort of the output you would get for explanations of like how good things are or how bad things are. Actually, let's look at the best ones. So here, these are the best indicators for each class. So that brings us to the end of this. Like I said, lots more to explore. I hope this is the starting point for many of you. I think there's a lot of exciting stuff to be done, a lot of low-hanging fruit, a lot of really great insights to be had, and a lot of fun. Very few things are as rewarding as getting a classifier to finally do what you want and look at the data, interpret the data, and see things on a massive data set that you would have never been able to go through by hand, and which took like 5 seconds to process with a machine learning tool. So with that, I say thank you. Thanks for the excellent questions. It was great. Thanks to the whole team for moderating, setting everything up, and being like a super supportive background team. I didn't have to worry about anything. Wonderful job, everybody. And yeah, with that, I think we come to the end.